There are moments when we gaze up at the night sky and feel the irresistible pull of the unknown. Not just a sense of wonder, but an ancient longing, as if the cosmos itself is whispering secrets, daring us to unravel the riddles sewn into the fabric of space-time. Among the many enigmas that haunt the universe, black holes, dark matter, cosmic voids, lies a particularly peculiar celestial phenomenon that defies conventional logic. Imagine a galaxy, millions of light-years away, radiating powerful beams not in the familiar twin jets aligned with its rotational axis, but rather in a mystifying X formation. These are the elusive, puzzling, and deeply fascinating X-shaped radio galaxies, cosmic anomalies that may hold hidden clues about the structure of the universe, the life cycles of galaxies, and even the violent ballet of supermassive black holes. But before we continue, subscribe to the channel so you don't miss out on any of these videos. These galaxies don't merely glow. They scream across the radio spectrum. Their existence challenges astronomers and theoretical physicists alike, suggesting violent histories, complex gravitational interactions, and mechanisms that remain far from fully understood. Unlike the more predictable forms of galactic architecture, spirals, ellipticals, and irregulars, X-shaped radio galaxies defy categorization. They're not just visual oddities. They are cosmic puzzles embedded in space, marking a place where something deeply unusual happened, or continues to happen. At the heart of these structures lies the interplay of unimaginable forces. We're talking about supermassive black holes, often billions of times the mass of our Sun, and jets of relativistic particles extending for hundreds of thousands of light-years. And yet, something disrupts this otherwise linear narrative. Instead of two symmetrical jets stretching out from the galactic center, we see two additional lobes or wings, forming a giant cosmic X. These secondary structures stretch out nearly perpendicular to the original jet axis, as if a second set of hands reached out from the galaxy's center. Why? How? The answer, as it turns out, may unlock deeper truths about the evolution of galaxies, the interaction between black holes, and even the subtle warping of spacetime itself. X-shaped radio galaxies are part of a broader class known as radio-loud active galactic nuclei, or AGNs. AGNs are among the most luminous persistent sources in the universe, often outshining the combined starlight of their host galaxies. Powered by supermassive black holes at their cores, AGNs draw in material from the surrounding galactic disk. As this material spirals inward, forming what's known as an accretion disk, it heats up and emits enormous amounts of energy across the electromagnetic spectrum. In many cases, this energy is funneled into two narrow jets that erupt outward along the poles of the rotating black hole, expelling matter at nearly the speed of light. These jets, when they interact with the intergalactic medium, form colossal radio lobes that are detectable using radio telescopes. In a typical radio galaxy, this jet structure is relatively straightforward, two opposing lobes aligned along a single axis. But in the case of X-shaped radio galaxies, something different is at play. Observations reveal a second pair of lobes, sometimes nearly as large or even larger than the primary pair, oriented at an angle that creates the unmistakable X pattern. The secondary lobes are generally less bright, often referred to as wings, but their presence is anything but secondary in significance. They are markers of disruption, relics of change, cosmic footprints of an extraordinary event or process. Astronomers have proposed several theories to explain the origin of these strange shapes. One leading hypothesis is that they are the result of a black hole spin flip event. In this scenario, a supermassive black hole at the center of the galaxy merges with another black hole, perhaps the remnant of a smaller galaxy consumed in a galactic merger. This collision, and subsequent gravitational dance, can cause the spin axis of the dominant black hole to reorient dramatically. When the spin axis shifts, so too does the direction of the relativistic jets. The old jets, now turned off but still lingering in space, become the wings, while the new jets carve fresh paths, creating the more dominant pair of lobes. Over time, this process leaves behind an X-shaped structure, a visual fossil of cosmic upheaval. Another theory suggests that the peculiar morphology arises not from a change in the black hole's spin, but from the backflow of energetic particles. In this model, the jets themselves remain stable, but the material they eject doesn't always escape cleanly into intergalactic space. Instead, some of it flows backward along the sides of the lobes, encountering resistance from the surrounding medium and spreading sideways, forming wings. This hydrodynamic backflow model doesn't require a merger or spin flip, but instead focuses on the interaction between the jets and the intergalactic medium, how the expelled matter collides, rebounds, and redirects in complex patterns. Yet another possibility is that the host galaxies themselves are rotating or precessing, subtly altering the orientation of the black hole's jet axis over millions of years. This idea, known as jet reorientation or precession, is supported by the fact that many X-shaped radio galaxies show signs of instability in their central structures. Precession could be caused by gravitational torques from surrounding structures, including stellar disks or nearby galaxies. If the jet axis shifts slowly over time, it could trace a sweeping arc through space, gradually creating secondary lobes that curve away from the primary axis. Despite the elegance of these theories, none of them fully account for every observed feature of X-shaped radio galaxies. Some galaxies show wings that are too symmetrical and sharply defined to be easily explained by backflow alone. Others display inconsistencies in jet power or orientation that don't fit neatly into a spin-flip scenario. The rarity of these galaxies, only a few dozen well-documented examples exist among the thousands of known radio galaxies, further complicates matters. Are they rare because the conditions that produce them are uncommon, or are we simply not looking at the right time or in the right wavelengths? Adding to the intrigue is the fact that these galaxies are enormous. Their wings often stretch for hundreds of thousands, sometimes millions, of light years across. That means whatever caused the X-shape was not a minor event. It required massive energies, sustained over long periods, and likely involved interactions on a galactic or intergalactic scale. In essence, the X is not a passive shape. It is a signature of conflict, change, and cosmic violence written in the language of light and magnetism. In some cases, high-resolution imaging reveals that the wings are not just extensions of the main lobes, but have distinct spectral and polarization characteristics. This suggests differences in age, composition, and magnetic field alignment. Studying these properties allows astronomers to effectively timestamp the different components of the galaxy, building a historical record of its energetic outbursts. In this sense, an X-shaped radio galaxy is like a time-lapse image of a black hole's turbulent past, a visual archive of shifts in direction, power, and structure. What makes X-shaped radio galaxies even more compelling is the possibility that they may be harbingers of gravitational wave events. If spin flips are indeed the result of supermassive black hole mergers, then these galaxies could be signposts marking where some of the most energetic gravitational wave emissions occurred in the ancient universe. Detecting and cataloging them could help scientists narrow their search for long-wavelength gravitational waves, which are notoriously difficult to observe with current instruments like LIGO or Virgo. In the future, space-based observatories such as the Laser Interferometer Space Antenna, LISA, may be able to detect the low-frequency gravitational waves emitted by these cosmic mergers, providing a new window into the lives and deaths of galaxies. Beyond astrophysics, the study of X-shaped radio galaxies also intersects with questions about cosmic topology and the nature of space itself. The way these structures bend and twist may hold clues about large-scale anisotropies in the universe, subtle variations in the structure of spacetime that are not yet fully understood. In that sense, these galaxies are not just oddities to be explained, but possibly keys to unlocking broader cosmological mysteries. Their very existence pushes the boundaries of our current understanding. X-shaped radio galaxies, in their majestic symmetry and startling scale, could be pointing us toward gaps in our astrophysical models, flaws in how we think galaxies grow, how black holes behave, and how energy flows through space on the grandest scales imaginable. They are not isolated phenomena. Rather, they may be interconnected with some of the most profound and elusive mysteries of the cosmos. They're messengers of change, carved by forces so immense that even light, the universe's most faithful informant, struggles to tell the full story. One of the most famous examples of an X-shaped radio galaxy is 3C 223.1. It was this object that drew attention to the very possibility that the traditional jet model might be insufficient. The peculiar X configuration of its radial lobes was too distinct, too orderly, and too powerful to be explained by conventional backflow alone. When radio astronomers pointed their telescopes toward 3C 223.1, they saw a structure that didn't merely deviate from expectations. It challenged the core assumptions behind jet formation, black hole activity, and interstellar interactions. Other examples such as 3C 403 and NGC 326 have been scrutinized in similar ways, revealing further inconsistencies, complexities, and often raising more questions than they answer. From a temporal perspective, we must also recognize how long these formations take to develop. The wings of an X-shaped radio galaxy don't appear overnight. They are the result of millions, even hundreds of millions, of years of energetic activity, shaped by interactions between light, plasma, magnetic fields, and space-time itself. We are seeing not just a picture, but a galactic autobiography, one told across epochs and woven with particle flows traveling at relativistic speeds. Every filament, every arc in the lobe's radio structure, is a sentence in a much longer story of galactic evolution. What makes the study of these galaxies even more captivating is the mystery surrounding their rarity. Out of thousands of observed radio galaxies, only a small fraction exhibit this X-shaped morphology. This statistical oddity has sparked speculation. Are we missing a large number of X-shaped galaxies because their wings fade more quickly than their main lobes, making them harder to detect? Or are they truly rare events, emerging only when a very narrow set of physical conditions align, such as precise black hole mass ratios, exact merger trajectories, and specific jet orientations? Could it even be that many galaxies go through an X-shaped phase, but only briefly, like a flash of brilliance in an otherwise linear evolution? There are models that attempt to simulate these scenarios. Computational astrophysicists have built sophisticated simulations, programming in the gravitational effects of galactic mergers, the magnetic interactions between plasma jets and ambient gas, and the dynamics of black hole spin. In some cases, these simulations produce X-shaped structures that closely resemble what we see through radio telescopes. But simulations are always approximations. They require assumptions. And more importantly, they only reflect what we think we know. The universe has a way of humbling us, of reminding us that even our best models are sometimes just elaborate guesses, useful but incomplete. And then there is the question of scale. It is one thing to talk about an unusual shape, but it is another to comprehend its true magnitude. The wings of some X-shaped galaxies stretch for over 1 million light-years across, more than 10 times the diameter of the Milky Way. These are not mere structural quirks. They are titanic sculptures shaped by raw energy, each wing an immense river of plasma traveling at a significant fraction of the speed of light, under the influence of powerful magnetic fields, and interacting with clouds of intergalactic gas that we can barely detect. If you could somehow stand at one end of the wing and look toward the galaxy's center, it would be like staring down a cosmic tunnel, thousands of times longer than our entire galaxy, filled with charged particles, radiation, and the residue of ancient galactic cataclysms. But the implications don't stop there. X-shaped radio galaxies might also be crucial to understanding the so-called spin alignment problem. The curious observation that the spin axes of certain black holes appear to align over vast distances, far beyond what current cosmological models would predict. If mergers and spin flips can reorient black holes in consistent ways, and if these events are more common than previously thought, they might help explain these cosmic alignments. In this way, X-shaped galaxies could act as markers, indicating not just individual histories, but perhaps revealing patterns in the evolution of large-scale structure in the universe. Moreover, the distribution of X-shaped radio galaxies could offer clues about the density and composition of the intergalactic medium. Since the visibility of radio wings depends on how jets and plasma interact with their surroundings, the clarity and brightness of these features can inform astronomers about the cosmic weather of the area. This means that studying these galaxies is not only a way to learn about the galaxies themselves, but also about the vast and nearly invisible medium that surrounds them, a kind of intergalactic archaeology. We also must consider their orientation. Some X-shaped galaxies have their wings perpendicular to the plane of the sky, while others are tilted or twisted in unexpected ways. This variation adds complexity to any unified theory. Why do some wings curve, and others remain straight? Why do some fade rapidly while others remain crisp and sharp for tens of millions of years? These differences may hint at a spectrum of processes, rather than a single mechanism. Perhaps multiple formation pathways exist, some due to black hole mergers, others to hydrodynamic backflow, and still others to jet reorientation. If so, each X-shaped galaxy might represent a unique case study in cosmic dynamics, a different type of transformation, a different kind of past. Even their host galaxies are worth examining. Many of them are giant elliptical galaxies, often located in relatively isolated environments. This raises questions about how often mergers occur in such settings, and what types of galaxies are likely to produce X-shaped structures. Are these galaxies particularly massive, leading to more intense jet activity? Or is there something about their histories, quiet and undisturbed for long periods, that makes them more likely to preserve the signature of a past merger? Interestingly, recent observations using low-frequency radio arrays such as LOFAR, Low-Frequency Array, and the GMARTI, Giant Meter-Wave Radio Telescope, have uncovered fainter and older wings in some galaxies previously thought to be typical double-lobed radio galaxies. This suggests that some of the galaxies we've categorized as normal may in fact have hidden X-shaped structures, invisible in higher-frequency radio surveys. It raises the possibility that X-shaped galaxies are not as rare as we think, but that their wings simply fade faster, or radiate at lower frequencies that we are only now becoming capable of detecting. As radio astronomy technology advances, we may be on the cusp of discovering an entire hidden population of these enigmatic formations. But for now, the riddle remains unsolved. Every new discovery leads to more questions. Are X-shaped radio galaxies evolutionary waypoints? Are they galactic fossils, frozen snapshots of an earlier cosmic drama? Or are they active participants in some still unknown universal mechanism, playing a role in structuring the observable cosmos in ways we cannot yet perceive? The allure of X-shaped radio galaxies lies not just in their aesthetic symmetry or their scientific mystery, but in their ability to remind us of the immensity of our ignorance. Each one is a paradox, symmetrical yet chaotic, structured yet enigmatic, bright yet fading. They stretch across space and time, whispering stories we only partly understand, hinting at events whose energy output dwarfs our entire solar system's lifetime emission. To study them is to acknowledge how little we truly know. And yet, in the pursuit of understanding these cosmic excess, we step closer to unveiling the underlying architecture of the universe itself. They are not just peculiar formations to be catalogued. They are cosmic question marks, pointing us toward answers we haven't yet dreamed of. Indeed, these celestial enigmas, the X-shaped radio galaxies, serve as interstellar markers on a much vaster and older roadmap than humanity has ever followed. Each one is like a fossilized scream across space-time, a testament to a violent past we can only observe through whispers of radiation. And the deeper we peer into their ghostly wings and powerful lobes, the more we begin to realize that their story may be inseparable from the very story of the universe itself. Let's dig even deeper into their mechanisms. Among the leading hypotheses surrounding their formation, one intriguing explanation is known as the spin-flip model. This model proposes that after a supermassive black hole merger, the resulting black hole rapidly changes its axis of spin. When this happens, the jets of plasma, once beaming in one direction, are suddenly redirected. The original jets, having blasted their way through space for eons, begin to fade, leaving behind those broad, ghost-like wings. Meanwhile, new jets erupt from the newly spun-up black hole, forming the prominent lobes we see today. This dual directionality gives rise to the X-shape. But this model, compelling though it is, depends on the assumption that black hole spin can change dramatically in relatively short time frames, and that such flips are strong enough to completely redirect relativistic jets. The physics of this process is not fully understood. Black holes are not like spinning tops we can see and poke. Their angular momentum is inferred from indirect measurements, and the dynamics of mergers are incredibly complex. How quickly can a black hole reorient? Can it happen abruptly, or is it more gradual? These questions remain open. Moreover, there's the jet reorientation model, slightly different but related, suggesting that black hole accretion disks, the disks of gas and dust spiraling into the black hole, shift due to external torques. This reorientation could be triggered not necessarily by mergers, but by instabilities or changes in the galactic environment. Such a shift would naturally alter the direction of the jets. The result? A new pair of radial lobes forming at an angle to the older, now fading ones. The pattern remains X-shaped, but the mechanism doesn't require a full black hole merger. Then we return to the hydrodynamic backflow model, which sees the X not as two distinct sets of lobes but rather as a result of how matter flows after being ejected. In this model, plasma from the active jets pushes outward into space, but instead of dispersing uniformly, it encounters resistance, from intergalactic gas or from remnants of previous jet activity. This resistance causes some of the energetic material to flow backward and sideways, forming the less intense but still visible secondary wings. It's almost as if the jets are carving through molasses, and some of that cosmic syrup spills over, shaping the wings behind them. This idea is fascinating because it makes the X-shape less about galactic catastrophe and more about the fluid dynamics of space itself, a subtle dance between motion and resistance, inertia and drag, magnetic field and interstellar wind. The backflow hypothesis, while elegant, still has some challenges. For one, it doesn't easily explain why the wings are sometimes just as prominent as the active lobes, or why they are often so sharply defined. If backflow alone were responsible, we might expect more irregularity, more asymmetry, than we observe in the most striking X-shaped galaxies. Perhaps most tantalizing of all is the suggestion that X-shaped radio galaxies could be more than just an astrophysical curiosity, that they might help detect gravitational waves on a galactic scale. Gravitational waves, ripples in spacetime caused by massive objects accelerating, are notoriously difficult to detect. But black hole mergers, especially supermassive ones, are among the most powerful generators of such waves in the universe. If the spin-flip model holds, and if the sudden reorientation of a black hole's spin axis is a direct consequence of a massive merger, then each X-shaped galaxy might be a fossil record of a gravitational wave event. They are, in this sense, the silent echoes of cosmic collisions, visible long after the waves themselves have passed. This connection is profound. It means that by cataloging and studying X-shaped galaxies, their distribution, morphology, brightness, and orientation, we may be able to reconstruct a history of ancient black hole mergers, mapping out a timeline of cosmic violence that no current gravitational wave observatory could detect. They become, in essence, a kind of galactic archaeology, allowing us to uncover events that happened hundreds of millions of years ago, far beyond the range of even our most advanced LIGO detectors. The implications don't stop there. If black hole mergers are indeed as common as these X-shaped galaxies suggest, this would force us to reconsider our models of galaxy formation and evolution. Galaxies don't just grow by accreting matter, they collide, they fuse, they cannibalize each other. And at their cores, these collisions leave behind monstrous consequences, black holes that devour one another and reshape the structure of their host galaxies. The X-shaped galaxies are like surgical scars, visible evidence of those central traumas. In fact, some researchers have proposed that X-shaped radio galaxies might be a transitional phase, not just between jet orientations, but between entire states of galactic life. After a merger, the black hole becomes re-energized, feeding again on surrounding gas, launching new jets. This resurgence could influence star formation rates, heat the surrounding gas, or even help regulate how much new material the galaxy can attract. Thus, the appearance of an X-shaped galaxy might signify not just a jet reorientation, but a full-blown rejuvenation of galactic activity, a kind of rebirth by fire. Now consider another layer: time. When we observe these galaxies, we are not seeing them as they are today, but as they were millions or even billions of years ago. The radio waves emitted by their lobes and wings travel across space at the speed of light, reaching us only after immense spans of cosmic time. Some of these galaxies might no longer exist in the same form. Their jets may have quieted. Their wings might have faded. But we are seeing their echoes, their ancient signatures still imprinted on the fabric of space. This temporal dimension gives X-shaped galaxies a unique philosophical resonance. They are not just remote, they are historical. They are messengers from the deep past, offering us brief glimpses into the life cycles of the cosmos. Each one is a frozen story, a fossilized drama written in plasma and light, speaking to us across eons. To study them is to look not just far, but deep, deep into the past, and deep into the nature of the universe itself. As we continue to discover more of these galaxies, especially with next-generation radio telescopes like the Square Kilometre Array, SKA, which promises unprecedented sensitivity, we may find patterns we couldn't detect before. Perhaps the wings of X-shaped galaxies encode subtle information about the environments in which they formed, or the particular parameters of the mergers that birthed them. We might even find transitional forms, galaxies that are in the process of forming their wings, or fading back to linearity, offering rare insights into the life cycles of radiolowed galaxies. Or perhaps we will discover entirely new morphologies that force us to once again rewrite our theories, shapes that don't fit into any existing model, that challenge our assumptions, and remind us that the cosmos is not obliged to conform to our categories. Because that's the truth at the heart of astronomy, and especially at the heart of mysteries like the X-shaped radio galaxies. The universe is not simple. It is not fully knowable. It is a grand tapestry woven from light, shadow, force, and silence. And sometimes, when we look at something as strange and wondrous as an X-shaped galaxy, we're not seeing an answer. We're seeing a question, one posed not in words but in structure. A question so immense, it spans 1,000,000 light years. A question written in the ancient script of jets and wings, lobes and radiation. A question we may spend centuries trying to answer. And maybe, just maybe, that's the point. But the question deepens when we begin to look beyond the morphology, beyond the shape of these enigmatic galaxies, and into the underlying cosmological context in which they exist. For instance, why do X-shaped radio galaxies appear to be relatively rare compared to other radio galaxy types? Is it simply an observational bias, due to the fading nature of the secondary lobes, or is it indicative of a rarer type of galactic event? And if the latter, then what precise conditions must align for an X-shaped galaxy to be born? To explore this, researchers are beginning to map out correlations between host galaxy properties and X-shaped features. Most X-shaped radio galaxies appear in elliptical galaxies, often giant ones, located in relatively dense environments like galaxy clusters. These environments are fertile grounds for mergers, collisions between massive galaxies that bring their central black holes into contact. The density of stars, the gravitational potential, and the surrounding intergalactic medium all play crucial roles in shaping the fate of the galaxy and its jets. This could suggest that X-shaped galaxies are not isolated curiosities, but integral players in the grander evolution of galaxy clusters and large-scale structure. Even more fascinating is the alignment, or sometimes misalignment, between the host galaxy's stellar light distribution and the orientation of the radio lobes. In many X-shaped galaxies, the wings, the older or secondary lobes, appear perpendicular to the major axis of the host galaxy's stellar bulge. This has led to speculations that the secondary lobes may expand into regions of lower gas density, where they encounter less resistance and therefore persist longer. But if the wings are simply backflow along the galaxy's minor axis, why do they maintain such sharp symmetry and often appear nearly as powerful as the primary jets? Such symmetry suggests some form of coherent mechanism, whether from spin reorientation or powerful feedback cycles, which creates not just structural echoes, but energy echoes, aftershocks of black hole activity rippling through cosmic time. These wings, then, are not passive leftovers. They may be active participants in shaping their galactic environment. This invites a deeper line of inquiry. Could X-shaped radio galaxies represent a kind of cosmic feedback loop? We already know that black holes can regulate star formation through AGN feedback, blasting out jets and winds that heat or expel gas, preventing it from collapsing into new stars. In X-shaped systems, where the direction of energy injection changes radically, might this feedback be even more profound? Imagine a galaxy being battered first along one axis, then another, with each phase of jet activity injecting turbulence, shock waves, and magnetism into the surrounding medium. Such a galaxy might be subject to episodic regulation, bursts of activity followed by periods of quiet, each resetting the evolutionary clock. In this way, X-shaped radio galaxies may serve as multi-phase feedback agents, more dynamically disruptive than their linear cousins. They may not just sculpt their halos, they may actively reshape the potential for future star formation, effectively acting as the architects of their own future. This cyclical behavior could also tie into the broader phenomenon of radio mode feedback, thought to be crucial in explaining why massive galaxies do not form stars indefinitely. Furthermore, there's the curious observation that the spectral ages of the wings often match or are slightly older than the primary lobes, suggesting either a rapid jet reorientation or a brief quiescent phase between jet cycles. This supports the idea that these features were created in rapid succession, not millions of years apart, but potentially within the same active phase of black hole accretion. Such synchrony deepens the mystery. How could a central engine redirect its jet axis so quickly, yet produce such coherent and powerful output in two entirely different directions? One tantalizing possibility is that these rapid changes are caused not by mergers, but by instabilities in the accretion disk itself. The inner region of a black hole's accretion disk, where magnetic fields are twisted to extreme degrees, might undergo sudden realignments. These magnetohydrodynamic instabilities could tilt the jet launching mechanism without the need for a full-scale merger. If so, then X-shaped galaxies could emerge not from cosmic collisions, but from internal chaos within the hearts of galaxies. There's also the theory that binary black hole systems, where two supermassive black holes orbit each other after a galaxy merger, might be responsible for some X-shaped forms. In these systems, the jet might precess, tracing out an arc over time due to gravitational torques from the companion black hole. This precession could lead to an apparent X-shape if the jets sweep through different directions over a sufficiently short timescale. In this view, the galaxy's X becomes a signature of duality, of a central engine not singular, but dancing in gravitational tension with another. If that's the case, then X-shaped galaxies could serve as signposts for binary black holes, a class of objects crucial for understanding both galaxy evolution and gravitational wave astronomy. The detection of such binaries has so far been elusive, especially for supermassive pairs. If X-shaped galaxies offer even indirect evidence of their existence, they could be invaluable in hunting down these cosmic couples, especially as future observatories like LISA, the Laser Interferometer Space Antenna, come online to detect low-frequency gravitational waves from supermassive black hole mergers. Moreover, some theorists have pushed the boundaries even further, asking whether exotic physics might be at play in X-shaped galaxies. Could features of these systems hint at deviations from standard general relativity? Could they reflect interactions between dark matter and baryonic matter on galactic scales? Or perhaps they reveal unknown behaviors of plasma in extreme magnetic and relativistic environments, conditions we can't replicate in any terrestrial lab. And if we go truly speculative, as astronomy sometimes invites us to do, we might even consider whether such peculiar morphologies could ever be artificial in origin. This idea, while on the fringe, has been entertained in the context of the search for extraterrestrial intelligence, SETI. Could advanced civilizations manipulate jets or magnetic fields to create vast cosmic structures, leaving beacons written across the sky in radio waves? It's unlikely, but as history shows, some of the greatest scientific breakthroughs began with a question that sounded absurd. Still, X-shaped radio galaxies, for all their majesty and mystery, are ultimately reminders of the untamed forces at the universe's core. Their shapes are not accidental. They are signatures of black holes that have collided, spun, flipped, and raged across epochs. They are echoes of physics too vast to witness directly, but precise enough to leave patterns we can decode. And their rarity does not make them less important. On the contrary, it hints at the special conditions under which the universe chooses to leave its more cryptic messages. As we turn more of our telescopes toward the sky, as arrays like Loafer, Meerkat, and the SKA chart the radio universe in exquisite detail, we will likely discover many more of these cosmic excess. Some will be bright and sharp, others faded and ancient. Each will offer a different clue, a different angle of approach to a problem as old as astronomy itself: how galaxies grow, evolve, and interact with the black holes at their cores. And maybe, just maybe, these galaxies, these monumental, glowing excess, are not just cosmic phenomena. They are crossroads. Places where the past meets the future. Where gravity meets radiation. Where silence meets the roar of ancient energy. And where we, standing on a pale blue dot, catch a glimpse of the raw creative fury that made the universe what it is. To further delve into the enigma of X-shaped radio galaxies, we must trace the intricate web connecting cosmic magnetism, relativistic plasma physics, and the evolutionary pathways of galaxies. At the heart of every X-shaped radio galaxy lies a supermassive black hole, surrounded by an accretion disk funneling matter inward while simultaneously launching twin jets outward at nearly the speed of light. These jets, composed of charged particles spiraling along magnetic field lines, extend for hundreds of thousands of light years, ultimately forming the radio lobes we observe. But what happens when the conditions at the core shift dramatically? In some systems, we observe evidence of jet quenching and reignition, a process by which the black hole temporarily halts its outflows only to resume activity on a new axis. This rapid realignment and restart could be a pivotal cause behind the X morphology, a celestial record of past and present jet orientations frozen in time. To understand how such changes occur, astrophysicists model the behavior of accretion disks under the influence of external torques. These torques might arise from misaligned gas inflows, perhaps the remnants of a cannibalized dwarf galaxy, or even from internal warping instabilities triggered by the black hole's own spin. In certain conditions, the accretion disk can decouple from the black hole's equatorial plane, resulting in a situation where jets are no longer aligned with the black hole's spin axis. This temporary misalignment can lead to jet directions shifting rapidly over cosmic timeframes, a mechanism known as the Bardeen-Pedersen effect. This theoretical model explains not just the angular disparity between primary and secondary lobes but also the sharp boundaries between them, which would be difficult to reproduce if the shift was gradual or if both jet directions coexisted over long periods. In other words, many X-shaped galaxies may have experienced an abrupt redirection of their jets due to a sudden shift in the spin axis of the central engine. In the backflow model, however, the morphology is shaped more by hydrodynamics than by black hole mechanics. As jets propagate into the intergalactic medium, some of the energy and material doesn't escape into space but instead flows back toward the host galaxy, following paths of least resistance. These backflows can then fan out perpendicular to the original jets, forming wing-like structures. High-resolution simulations have shown that such backflows are particularly prominent in environments with pressure anisotropy, where the external medium offers differing resistance in different directions. Backflow models are compelling because they do not require a black hole merger or a spin flip, only sustained jet activity and an asymmetric environment. Yet they struggle to explain the high degree of symmetry observed in many X-shaped radio galaxies. If backflow is the sole cause, why are the wings so balanced and collimated in many examples? Nature is rarely that precise without a guiding force. This tension between models has led to a hybrid perspective. Perhaps both processes contribute. A spin flip could realign the jets, while residual energy from the older jets gets redirected by backflows, forming wings. This combined mechanism would explain not only the symmetry but also the aging spectral signatures and morphological persistence of the wings, long after the central engine has changed direction. Spectral aging itself is a critical clue. By analyzing the synchrotron emission across different frequencies, astronomers can estimate the energy loss of relativistic electrons in the lobes. These estimates provide a kind of cosmic timestamp, revealing when each part of the radio structure was last energized. In many X-shaped galaxies, The wings are older but not by much, supporting the idea that the secondary and primary lobes were created in quick succession. But there are exceptions. Some galaxies show wings that are brighter or more extended than the active lobes, flipping expectations on their head. This has led to the concept of wing-dominant XRGs, where the secondary lobes appear more prominent than the primary ones. Such configurations challenge all simple models and hint at multiphase activity, where older jets remain active for longer, or where environmental factors boost their visibility long after formation. One particularly famous example is the galaxy 3C 223.1, whose wings are almost as bright as its primary jets. Its structure has been studied extensively, revealing a complex interplay between spectral age, morphology, and the surrounding cluster environment. The case of 3C 223.1 highlights the limitations of one-size-fits-all explanations and reinforces the idea that X-shaped galaxies are not a monolithic class, but rather a family of objects linked by similar visual signatures born from potentially diverse causes. Furthermore, as more data becomes available from sensitive radio telescopes like LOFR, GMRT, and the upcoming Square Kilometre Array, SKA, researchers are identifying X-shaped morphologies in less luminous galaxies, suggesting that the phenomenon may be more common than previously thought. These faint wings, often overlooked in earlier surveys, might reveal a hidden population of galaxies undergoing jet reorientation or backflow, a silent majority of XRGs veiled by technical limitations. The implications stretch far beyond morphology. If X-shaped galaxies indeed trace black hole mergers or reorientation events, they may serve as probes of black hole spin evolution, a key parameter in high-energy astrophysics and cosmology. The spin of a black hole determines how efficiently it can launch jets, how it interacts with its accretion disk, and how it influences the surrounding galaxy. Tracking spin changes across cosmic time could offer insight into galactic assembly histories, including how often major mergers occur and what kinds of systems result. There's also a tantalizing intersection between X-shaped galaxies and the detection of low-frequency gravitational waves. If black hole binaries are responsible for jet reorientation, and if those binaries are common enough, they should produce a background hum of gravitational radiation, detectable by projects like pulsar timing arrays, PDAs. In fact, recent data from collaborations like NANOGrav and EPTA hint at the presence of such a signal. Could the population of XRGs be offering a visual counterpart to this auditory whisper from the fabric of spacetime? Even more provocatively, studying the distribution of XRGs across redshifts can reveal how jet dynamics have evolved across cosmic history. Are these galaxies more common at certain epochs? Do they cluster in particular environments, near the centers of clusters, or in isolated halos? The answer to these questions could help distinguish between competing models of jet formation and black hole growth. And beyond all these technical insights, X-shaped galaxies speak to the sheer creative violence of the universe. These are not gentle objects. They are titanic storms of energy and magnetism, launched from the deepest gravitational wells in existence. Their structure is not static but dynamic, shaped by momentum, friction, feedback, and fusion. They are a kind of celestial graffiti, scribbled across millions of light years, recording not just what a galaxy is, but what it has endured. Perhaps one of the most poetic aspects of X-shaped radio galaxies is that they are cosmic palimpsests, layered records of activity that has come and gone. The wings are ghosts of a previous alignment, still glowing after millions of years. The primary lobes are the present moment, crackling with energy and purpose. And between them lies a story of upheaval, of black holes spinning and merging, of plasma racing through intergalactic space, and of nature writing its history in the language of light and magnetism. These celestial structures, X-shaped radio galaxies, stand as silent testaments to the ever-evolving architecture of the cosmos. As we continue peeling back the layers of their mystery, one aspect becomes increasingly clear. They are not anomalies, but rather evolutionary bookmarks in the life stories of galaxies that have undergone immense transformation. From galaxy mergers to shifts in black hole spin, from massive ejections of relativistic plasma to the lingering echoes of ancient jets, each X-shaped formation carries a signature far more intricate than the eye, or even the telescope, can immediately see. A question that naturally arises is, what triggers such rapid jet realignment or significant environmental changes to allow for the X-shape to emerge in such symmetry? One line of inquiry focuses on galaxy interactions in dense environments. In these crowded regions of space, galaxies are not isolated islands but swirling in gravitational dance with many neighbors. These interactions can lead to not only mergers but also to significant angular momentum exchange with the inflowing intergalactic medium. When a black hole is suddenly fed material from a misaligned plane, like from a passing dwarf galaxy, it could spin up and shift its jet axis without undergoing a full merger. This would simulate the effect of a jet realignment and lead to an X-shaped morphology without the need for a binary black hole. Alternatively, the spin-flip scenario remains one of the most dramatic interpretations. Imagine two galaxies merging, each with a central black hole. Over millions of years, these two black holes spiral toward one another, releasing energy in the form of gravitational waves. Just before the merger, complex torques can cause the secondary black hole to become dynamically dominant, especially if it possesses a high spin. When the black holes coalesce, the resulting merged black hole inherits a spin that may be significantly misaligned with its previous direction, instantly changing the orientation of any new jets. This spin-flip theory aligns well with numerical relativity simulations, which show that post-merger recoil velocities can be substantial, sometimes ejecting the black hole entirely from its galaxy. But when recoil is moderate, and the black hole remains, it can realign its jets to the new spin, effectively writing a new line across the cosmic canvas. An area of growing interest is how the magnetic field topology of a host galaxy influences jet dynamics. Jets are believed to be powered by the Blandford's-Najek mechanism, where rotating black holes drag surrounding magnetic field lines, converting rotational energy into electromagnetic outflows. The shape, strength, and connectivity of these fields determine how jets behave, whether they are narrow and stable or broad and prone to precession. In X-shaped galaxies, misalignments between the black hole's spin axis and the magnetic field direction could produce unstable or precessing jets, which in turn might trace out the X-shape over time. Radio astronomers are now increasingly able to map the magnetic field structures in these galaxies using polarimetry, which measures the orientation of radio waves and reveals the alignment of electrons spiraling through magnetic fields. Early data suggests that polarization vectors in the wings of XRGs tend to align differently from those in the active lobes, hinting at distinct episodes of jet activity under changing magnetic and gravitational conditions. These findings suggest not just a change in jet direction, but potentially a reconfiguration of the entire central engine. And yet, even with all this understanding, the frequency and distribution of X-shaped radio galaxies remain curious. Only a small fraction of known radio galaxies exhibit the characteristic X-shape, though the true number may be significantly undercounted due to observational limitations. Most surveys, like those conducted by the VLA or FIRST, were designed for general-purpose imaging and may not have had the depth or resolution to capture faint wings. But as deep learning techniques and automated morphological classifiers are applied to huge sky surveys like those from LOFR, MEERKAT, and eventually the SKA, we are discovering more faint XRG candidates, some barely distinguishable from noise, others hidden behind bright foreground emissions. This leads to a fascinating thought. Could X-shaped radio galaxies be more common than we think, only obscured by our limited tools and methods? If they are indeed more frequent, it could radically alter our understanding of how often black hole mergers, spin realignments, or jet reorientations occur. It might also imply that such dramatic events are not rare accidents but fundamental processes in galaxy evolution, events that every large galaxy may go through at least once in its lifetime. Another emerging area of interest is the relationship between XRGs and double-double radio galaxies, DDRGs. DDRGs are systems where two pairs of lobes are aligned along the same axis, likely representing two distinct episodes of jet activity. Some astronomers propose that DDRGs might be evolutionary cousins of XRGs, galaxies that underwent reactivation but without significant jet axis change. Comparing the population statistics, lobe dynamics, and spectral aging properties between DDRGs and XRGs could help create a continuum model of radio galaxy evolution, where XRGs represent cases of angular disruption and DDRGs represent cases of angular stability. Adding another layer of complexity, some XRGs display Z-shaped or wing-bent morphologies, where the wings are curved rather than straight. This suggests additional influences from bulk gas flows, such as those generated by galaxy cluster winds, motion through the intra-cluster medium, or sloshing from previous merger events. These bent wings could serve as tracers of motion, giving us clues about the host galaxy's trajectory over cosmic timescales. In this way, the wings of XRGs may function not only as records of past jets but also as indicators of large-scale galactic kinematics. The multidisciplinary study of XRGs, therefore, sits at a crossroad between relativistic astrophysics, cosmology, galaxy evolution, magnetohydrodynamics, and gravitational wave astronomy. These galaxies serve as natural laboratories, providing insight into physical regimes far beyond human reach, environments with pressures, energies, and field strengths we cannot replicate on Earth. And yet, by decoding their structures, we extract timeless narratives from the silent radio whispers of the universe. Perhaps the most profound realization is that these galaxies are not just scientific curiosities, but fossils of change. They show us that the universe is not static, not serene, but fundamentally dynamic. Even entities as immense and seemingly immutable as galaxies are subject to upheaval, to transformation, to moments of violent rebirth and quiet reconfiguration. The elegant symmetry of an X-shaped radio galaxy is not just a visual oddity. It is a monument to an ancient upheaval, a moment when the cosmos shifted direction, and the scars of that event remain etched in the radio sky, glowing faintly across the void. As we gaze into these vast crucibles of transformation, we are not merely observers. We are participants in a larger narrative, one that binds black holes, stardust, light, and time into a single, coherent saga of cosmic evolution. X-shaped radio galaxies invite us to look deeper, to wonder harder, and to acknowledge that even in a universe governed by laws, there is still room for mystery. These X-shaped radio galaxies, cosmic beacons etched into the silent fabric of the universe, are not just indicators of high-energy astrophysical phenomena. They are, in a profound sense, windows into time itself. Their very structure, spanning hundreds of thousands or even millions of light years, preserves the ancient aftermath of cataclysmic shifts in galactic dynamics. Every arc of radio emission is a chronicle, and each deviation in lobe symmetry whispers of gravitational convulsions and reoriented black hole engines from millions of years ago. As observational technology sharpens and theoretical models become more sophisticated, a deeper story begins to take shape. One element of this emerging story involves the feedback loop between black hole activity and host galaxy evolution. We now understand that the active galactic nucleus, AGN, of a galaxy, powered by a supermassive black hole, can profoundly affect the rate of star formation in the host galaxy. Jets launched from the black hole can heat the surrounding gas, preventing it from cooling and collapsing into stars. This process, known as AGN feedback, regulates the growth of massive galaxies and shapes the evolutionary trajectories of galaxy clusters. In the context of X-shaped radio galaxies, this feedback mechanism might be especially dynamic. During the period of jet reorientation or spinflip, multiple outflow directions could emerge in a relatively short span of cosmic time. This multidirectional jet emission could lead to chaotic heating and turbulence in the interstellar and circumgalactic medium, further disrupting gas inflow and star formation cycles. In effect, XRGs may represent a heightened state of galactic feedback, where not just the presence of jets, but the dramatic change in their orientation amplifies their disruptive power. What's particularly fascinating is that in some XRGs, the wings, those secondary, now inactive lobes, may outshine the current active lobes in certain wavelengths. This suggests that the past episode of activity was either more powerful or lasted longer. These relic lobes, full of aged electrons that have lost energy over time through synchrotron radiation and inverse Compton scattering, still glow faintly in the radio spectrum. Scientists are beginning to treat these wings as archaeological features, using their spectral properties to reconstruct the ancient activity of now quiet black holes. To better understand this, astronomers employ spectral aging analysis, a method that assesses how much energy has been lost by relativistic particles in radio lobes over time. By comparing the spectra of the active and wing lobes, researchers can estimate the timescale of jet realignment, the duration of each active phase, and the interval between successive jet activities. Early studies suggest that the realignment process may occur on timescales of tens of millions of years, an instant in cosmic terms, but enough to leave a permanent mark in the galaxy's structure. Beyond just observing these lobes, astronomers are beginning to simulate them with increasing fidelity. Hydrodynamic and magnetohydrodynamic (MHD) simulations now model how jets evolve in 3 dimensions when they interact with anisotropic galactic environments, rotating accretion flows, and complex magnetic field configurations. Some simulations recreate the X-shape without invoking a spin flip, simply by placing a symmetrical jet in an elliptical atmosphere with pressure gradients. Others require a full merger scenario, where angular momentum from an infalling black hole shifts the jet direction. The key takeaway from these simulations is that X-shaped morphologies may emerge from a combination of factors, not a single mechanism. In some galaxies, the wings are pure backflows, relativistic plasma flowing backward after hitting a shock in the intergalactic medium. In others, they are fossil lobes from a previous jet axis. And in a rare few, they may be hybrids, where ancient jet material is reaccelerated or reshaped by environmental winds or sloshing cluster gas. This diversity of formation pathways challenges the idea of a single origin model. Instead, scientists are increasingly proposing a taxonomy of XRGs, classifying them based on observable features like lobe brightness, symmetry, polarization structure, and spectral steepness. The goal is to map out evolutionary trees, where each type of XRG represents a different stage or outcome of black hole and galaxy interaction history. It's a grand effort to not just label the galaxies we see, but to reconstruct the astrophysical dramas that produce them. The stakes of this research reach far beyond academic classification. Understanding XRGs could yield vital insights into gravitational wave astronomy. If many of these galaxies are the product of black hole mergers, then each one is a potential fossil record of a past gravitational wave event. The gravitational waves themselves may no longer be detectable, having rippled outward and dissipated into the cosmic sea, but their architectural echo remains in the sky, in the geometry of these vast X-shaped ghosts. And as the field of gravitational wave detection matures, with upcoming missions like LISA, Laser Interferometer Space Antenna, expected to detect supermassive black hole mergers, we may finally begin to correlate current radio observations with past gravitational wave events. In other words, astronomers could match an observed XRG to a detected wave signal and confirm the precise mechanism that formed the galaxy's structure. It would be a convergence of disciplines, radio astronomy meeting relativistic physics, each filling in the gaps of the other. Another question looms large in this cosmic inquiry: what happens after the wings fade? As the inactive lobes dim with age, they eventually dissipate into the surrounding space, leaving behind only the newer, active jets. Does the galaxy then return to looking like a conventional double-lobed radio galaxy? Or does the history of realignment forever change the galaxy's central dynamics, perhaps making it more prone to future disruptions? Do galaxies that undergo such reorientations multiple times develop more complex morphologies, Y-shaped, S-shaped, or even ring-like structures? In fact, there is growing evidence that morphological transitions between radio galaxy classes may be more fluid than previously thought. A single galaxy may cycle through multiple forms: compact, double-lobed, triple-source, X-shaped, double-double, as it evolves, interacts, and accretes. This dynamic view of galactic morphology has prompted some astronomers to rethink classification systems entirely, moving toward time-dependent evolutionary maps rather than static labels. This evolving perspective speaks to a larger truth: the universe is not a museum of isolated phenomena but a continuum of transformations. Every X-shaped radio galaxy we observe is a frame in an unfolding movie, one that spans billions of years and bridges disciplines, from plasma physics to relativity. Each wing, each jet, each ripple of radio emission is a cipher. And slowly, we're learning how to read it. As our instruments become more sensitive and our minds more open to the vast range of cosmic phenomena, we stand on the edge of a new era. The next generation of radio surveys, conducted by the Square Kilometre Array, the INGVLA, and space-based missions, will unveil thousands more of these X-shaped enigmas, many dimmer and older than anything we've seen before. These ancient structures will speak to us from the edges of time, their faint emissions whispering tales of black holes that danced, collided, and changed the fate of galaxies. And when we listen, truly listen, to these echoes in the radio sky, we are not merely uncovering scientific data. We are hearing the deep narrative of the cosmos, one shaped not just by gravity and magnetism, but by time, memory, and cosmic evolution itself. The deeper we probe into the mystery of X-shaped radio galaxies, the more we begin to realize that they are not anomalies. They are key pieces of a larger cosmic puzzle. A puzzle that connects not just galaxy morphology, but also the fundamental physics of black holes, the influence of dark matter, the motion of intergalactic gas, and the very architecture of the universe. Every time a galaxy's jet changes direction, every time wings of radio plasma drift outward into the void, we witness a kind of astrophysical punctuation mark, a statement made in energy, distance, and time. What makes XRGs particularly compelling is their rarity. In the cosmic census of radio galaxies, only a small percentage show this distinctive X-shaped pattern. Yet this scarcity is not a limitation, it is a clue. Why are they so rare? Is it because the conditions required to produce them are uncommon? Or is it because they exist for only a brief cosmic moment, quickly fading into more conventional shapes? Or is it possible that we've only scratched the surface, that many more XRGs are hidden in the noise of our limited-resolution radio surveys, waiting to be uncovered by future instruments? These questions have driven astronomers to develop pattern recognition algorithms and machine learning models that can comb through enormous radio datasets looking for candidate XRGs. With tools like convolutional neural networks, researchers are training computers to recognize subtle morphological cues, faint wings, bent lobes, hidden symmetry breaks, that might escape the human eye. These models, applied to surveys like FIRST, faint images of the radio sky at 20 centimeters, and the more recent LOW-TSS, Low for 2 meter sky survey, have already identified dozens of new X-shaped structures. And as the training improves, we could be on the brink of discovering hundreds, or even thousands more. But it's not just quantity that matters. It's what they tell us collectively. With enough examples, astronomers can begin to test population-level theories. Are XRGs more common in galaxy clusters or in isolation? Do they prefer certain types of host galaxies, ellipticals over spirals, or those with massive bulges and old stellar populations? Is there a statistical correlation between XRGs and galaxy mergers, or with the presence of companion galaxies and disturbed halos? Already, some patterns are emerging. XRGs tend to be hosted by giant elliptical galaxies, often at the center of galaxy groups or clusters. These are environments rich in hot, X-ray emitting gas, ideal for preserving the ghostly wings of ancient radio jets. Furthermore, many XRGs seem to reside in galaxies that show signs of recent disturbance, shells, ripples, asymmetries in starlight, suggesting a history of mergers or gravitational interactions. This reinforces the idea that the X-shape could be the signature of a recent galactic upheaval, etched across millions of light-years in radio light. To understand these formations in their broader context, we must consider the cosmological timescale. Galaxies, and the black holes at their centers, evolve over billions of years. The processes that create an XRG may span epochs longer than human civilization has existed. A jet turns on, blows bubbles into the surrounding medium, and fades. Then the black hole reorients, and a new pair of jets erupts in a different direction. Each step might take tens or hundreds of millions of years. From our brief moment of observation, we see only the snapshot, never the full movie. But even this snapshot is profound. Consider what it takes for a supermassive black hole, often billions of solar masses in size, to change its spin axis. This isn't a simple process. The inertia of such a colossal object resists change. It requires a titanic injection of angular momentum, likely from a merger with another black hole or a massive infall of misaligned gas. In such scenarios, the black hole's spin vector compresses, tilt, or flip entirely, a process predicted by general relativity and described in the physics of length-stirring precession. This brings us to another potential smoking gun, the double-double radio galaxies (DDRGs). These are galaxies that show not just one, but two distinct pairs of radio lobes, often aligned along the same axis. In some cases, a faint third pair emerges at a different angle, creating a kind of triple jet structure. These could be transitional objects, galaxies caught in the act of reorientation. They might even be evolutionary precursors or descendants of XRGs, giving us a continuum of forms from straight-line jets to fully cruciform structures. To unravel this, astronomers are now conducting multi-wavelength observations, not just in radio, but in optical, infrared, X-ray, and gamma rays. Each wavelength tells a different part of the story. X-rays reveal the hot gas environments that shape jet dynamics. Infrared shows us the dust and cold gas that fuel black hole accretion. Optical observations trace stellar population ages and merger remnants. And gamma rays, though rarer, provide insights into the most energetic particles accelerated by shocks within the jets. One recent discovery from this multimodal approach is the link between XRGs and binary supermassive black holes, SMBHs. In a few rare cases, observations suggest that a galaxy may host two closely orbiting black holes, remnants of a galaxy merger not yet fully coalesced. If one of the black holes is active and the other dormant, or if they take turns being active, the resulting jet structures could be offset, misaligned, or even alternating, creating a dynamic morphology that mimics or contributes to the X-shape. These dual black hole systems are more than curiosities. They are potential sources of low-frequency gravitational waves, the kind that LISA and pulsar timing arrays like NANOGrav are trying to detect. If we can identify galaxies that are both XRGs and gravitational wave sources, we will have found celestial laboratories, places where we can study, in real time, the final stages of black hole mergers and their cosmic consequences. And still, questions remain. Could there be more exotic explanations for the X-shape? Some theorists have proposed speculative ideas. Perhaps intergalactic magnetic fields, twisted and tangled across megaparsecs, play a role in deflecting or bifurcating the jets. Or maybe dark matter substructures, invisible clouds that tug on the jets gravitationally, could sculpt the strange angles we observe. While there's no definitive evidence yet, these ideas remind us of a humbling truth. We still don't fully understand the cosmic environment in which these galaxies evolve. Even the shape itself invites symbolic reflection. In a universe governed by entropy, where most systems tend toward disorder, the X-shaped radio galaxy stands as a moment of eerie symmetry. It is a fleeting equilibrium between past and future, between what once was and what is now. It is, in a way, a cosmic scar, a reminder of violence long past, but never forgotten, etched into the very geometry of space. Perhaps that's why they captivate us. Because they are not just objects of study, they are testaments to transformation. Galaxies that once blazed one path through space, only to be jolted into a new direction. Black holes that once fed quietly, then suddenly flared into life. Forces that once flowed in alignment, now skewed and reshaped by time, mass, and momentum. And as we peer deeper into the radio sky, catching more of these strange crosses glowing faintly among the stars, we are drawn not just to their mystery, but to their message. A message that says the universe is not static. It is dynamic, chaotic, beautiful. And sometimes, when the conditions are just right, it leaves behind patterns, perfect, haunting, and full of meaning. These haunting X-shaped forms, cast like celestial runes against the void, compel us to rethink our understanding of galactic life cycles. While we often depict galaxies as stately, spinning disks evolving predictably over billions of years, X-shaped radio galaxies are dramatic evidence that chaos, collision, and redirection are integral to their evolution. The very existence of such galaxies is a reminder that the cosmos is not a serene backdrop but a turbulent, shifting arena. One of the most compelling aspects of studying XRGs is how they force us to consider time and memory on a galactic scale. The wings that stretch away from their central cores are not merely structural artifacts, they are the fossils of past cosmic events. These wings are ancient jets, ejected millions of years ago, now dimmed and drifting, but still glowing faintly in radio frequencies. They are the remnants of a black hole's previous orientation, a memory of a time when it pointed in a completely different direction. This makes XRGs a kind of time machine. By studying the length, curvature, and brightness of their wings, astronomers can estimate how long ago the reorientation occurred, how fast the jets moved, and how the surrounding environment resisted or absorbed their energy. Every XRG, then, becomes a case study in cosmic archaeology. It's not just about what we see now, it's about reconstructing what happened millions of years ago to make it so. These reconstructions are not simple, though. They require sophisticated simulations and relativistic jet modeling, often involving the equations of magnetohydrodynamics, MHD. These simulations must account for jet composition. Are they made of electrons and positrons, or heavier ions? Jet velocity, often approaching the speed of light, the density and pressure of the intergalactic medium, and the magnetic fields involved. Only by fine-tuning these parameters can astronomers produce synthetic images that match the X-shaped structures we observe. In recent years, powerful simulation engines, such as those run on high-performance computing clusters and GPU-based architectures, have begun to yield more realistic models of jet behavior in changing environments. These show how jets can bend, break, or reorient in response to shifts in black hole spin or surrounding gas flows. Some simulations suggest that even a relatively small disturbance, like a dense gas cloud falling into the galactic nucleus, can create enough torque to shift the axis of the central engine. What's even more fascinating is that these shifts might happen more frequently than we think. In the traditional view, we imagine black holes as stable engines, their jets fixed in space. But if the central engine is constantly affected by its environment, accreting gas from chaotic directions, merging with smaller companions, experiencing turbulence from nearby stellar explosions, then its orientation may be in a perpetual state of flux. Perhaps what we call X-shaped is just one frame in a movie we've never seen in full. And this ties into a much broader, deeper cosmic narrative, the concept of AGN duty cycles. Active galactic nuclei are not always active. They flare into life, spewing jets and radiation, then fade into dormancy. Sometimes they restart. These cycles may be triggered by external events, like mergers or tidal interactions, or by internal feedback loops where the energy output regulates future accretion. In this framework, XRGs might represent restart events, moments when a previously dormant nucleus reignites, but in a different direction. Another theory posits that these changes are due not just to orientation, but to precession. Much like a spinning top wobbles as it slows, a supermassive black hole with an asymmetric accretion disk might experience torque that causes its jet to sweep out a cone over time. If that cone widens or tightens depending on the mass inflow, it could trace out shapes that, when viewed from Earth at just the right angle, appear X-shaped. This raises intriguing observational challenges. Are we really seeing an X in space, or is it an artifact of perspective, a kind of astrophysical illusion shaped by projection effects? In a three-dimensional universe viewed from a fixed two-dimensional plane, many structures can take on deceptive forms. Some researchers suggest that a subset of XRGs may not actually be shaped like XS in space, but only appears so because we're viewing a double-lobed jet system from an unusual angle. To resolve this, astronomers rely on polarization data, which provides information about the direction of magnetic fields in the jets and wings. By analyzing how radio waves are polarized, how their electric fields align, we can infer the orientation of the structures in 3D space. In many cases, this data confirms that the wings are real physical extensions, not just line-of-sight projections. But even with better data and modeling, the ultimate cause of the X-shape may differ from case to case. This leads to the possibility that XRGs are not a single class of objects, but a phenomenological grouping. In other words, many different processes, jet reorientation, spin flip, precession, jet deflection by dense gas, or even black hole binaries, can produce similar-looking structures. The X-shape may be a convergent morphology, arising from multiple unrelated pathways. This realization has huge implications for our understanding of galaxy evolution. It suggests that galactic cores are far more dynamic and responsive than we once assumed. It also implies that black holes can retain memories of their past states, not in their structure, but in the shape of the space around them. That memory is broadcast across millions of light years, like a signal from a forgotten era, preserved in the whisper of radio waves. From a technological perspective, the study of XRGs is poised to leap forward in the next decade. The Square Kilometre Array, SKA, once operational, would provide unprecedented sensitivity and resolution in radio frequencies. With it, astronomers hope to detect even the faintest wings and lobes, expanding the catalog of known XRGs by orders of magnitude. These new discoveries could help determine whether the X-shape is a brief, rare stage, or a recurring feature in many galaxies' lifespans. At the same time, new infrared and X-ray telescopes will probe the host galaxies themselves with more detail. They will help us map out the stellar populations, dust lanes, nuclear activity, and signs of recent mergers. By combining this multi-wavelength data with machine learning classification, astronomers aim to build a robust taxonomy of XRGs, linking shape to cause, structure to history. And while the data accumulates, the mystery endures. X-shaped radio galaxies are the crossroads of many astrophysical domains: jet dynamics, black hole physics, galactic mergers, cosmic magnetism, and cosmological evolution. Each one is a question mark written in fire across the sky, a reminder that the universe is vast not just in space, but in complexity. They show us that the cosmos is not a place of static symmetry, but a realm of drifting vectors, shifting alignments, and persistent echoes of change. What makes these galaxies so compelling is not just their rarity or beauty, it's their implication. That galaxies, like people, carry the scars of their past. That energy once spent leaves traces. That trajectories are not always straight. That change, cataclysmic, sudden, and unpredictable, can reshape even the most massive forces in the universe. They are cosmic emblems of transformation, and in their silent shapes, they speak volumes. And so, the tale of X-shaped radio galaxies deepens, not just into their physics, but into their profound symbolic role in our cosmic understanding. In many ways, they function as galactic palimpsests, celestial manuscripts written over time, where newer lines overwrite the old, yet traces of earlier stories remain legible. The wings are these older scripts, left behind after the pen of relativistic jets has moved on, redrawn, or even been torn away and rewritten by the turbulent hand of cosmic time. One intriguing area of ongoing research is the role of spin alignment between supermassive black holes and their accretion disks. When a black hole gains mass, whether from infalling gas or a merging companion, it doesn't just grow, it also changes direction. This is because angular momentum, like mass, must be conserved. If new material enters from a different direction than the previous inflow, it can slowly torque the black hole's spin axis. This realignment process, especially after a galaxy merger, can produce a delayed but sudden flip in jet direction. Some theoretical models show that if the change in angular momentum is significant enough, the jet axis may precess gradually at first, and then jump abruptly, creating the classic X pattern. A particularly exotic variant of this theory involves spin flips from gravitational wave recoil. When two black holes merge, they emit gravitational waves, ripples in spacetime that carry away momentum. If this emission is asymmetric, due to unequal masses or spins, the resulting black hole can experience a powerful kick, potentially moving at thousands of kilometers per second. If this kick also alters the spin axis, the new jet direction could be radically different from the old. In this case, the old jets become the wings, and the new ones form the active lobes. This paints XRGs not just as structures, but as gravitational footprints of ancient cataclysms, silent witnesses to black hole mergers that happened hundreds of millions of years ago. The observational evidence for these scenarios is mounting, especially as we begin to detect more compact symmetric objects, CSOs, and double-double radio galaxies, DDRGs. These classes, while distinct from XRGs, often show similarities, symmetrical lobes, signs of multiple jet episodes, and varying orientations. Some astronomers suggest that these galaxies form a continuum of radiomorphology, where XRGs occupy one corner of a much larger, more complex landscape of jet behavior. In fact, a new idea gaining traction is that the X-shape is a transitional stage. Imagine a galaxy undergoing a black hole merger. The event stirs up the core, redistributes angular momentum, and causes a temporary phase of chaotic jet behavior. During this phase, the old jet direction lingers, the new direction emerges, and both are visible in the radio map. Over time, the old wings fade, the new jets dominate, and the galaxy moves into a more standard double-lobe morphology. But during the brief transition, perhaps only a few million years long, it appears as an XRG. If this is true, then X-shaped galaxies are even more precious, fleeting windows into an unstable evolutionary moment, a cosmic metamorphosis caught mid-transformation. Yet this view raises an uncomfortable question: how many XRGs have we missed? The majority of radio galaxy surveys have historically focused on bright, simple structures, powerful jets, and large lobes. But the wings of XRGs are faint, often lying well below the detection threshold of older instruments. Moreover, they can be easily confused with background noise or overlooked due to selection bias, the tendency of surveys to catalog only the clearest, brightest examples. Now, with deeper sky surveys and better image processing algorithms, more XRG candidates are being uncovered, and the numbers are growing. This could imply that the phenomenon is more common than previously believed, hidden in plain sight by our technological limitations. Adding to this growing body of research is the importance of host galaxy morphology. XRGs are almost always found in giant elliptical galaxies, often at the centers of galaxy clusters or rich environments. These galaxies are known for their dynamic histories, multiple mergers, extensive halo gas, and active black hole feedback. This raises the possibility that environmental factors, like the shape and density of the surrounding medium, may influence jet bending or reorientation. For instance, an asymmetric gas halo could deflect a jet as it exits the nucleus, especially if the surrounding gas is denser in one direction. Over time, this could produce a misaligned set of lobes. Other theories suggest hydrodynamic backflows as the cause. In this scenario, the relativistic jets, upon colliding with the intergalactic medium, create pressure waves and turbulent eddies. Some of this energy flows backward along the sides of the jet path, creating extended plumes that appear as wings. These wings are not relic jets at all, but rather radio-bright byproducts of fluid instabilities. Though this model doesn't require a jet reorientation, it does require a very specific set of conditions: powerful jets, dense ambient medium, and large-scale symmetry. For this reason, it may explain only a subset of XRGs. What's fascinating is that multiple mechanisms may operate simultaneously, or sequentially. A galaxy might experience a merger, causing a spin flip. The new jets punch through the dense core, interact with the medium, and form turbulent backflows. Later, a secondary infall of gas might trigger jet precession. In such a scenario, an X-shaped radio galaxy could result from a complex choreography of at least 3 different astrophysical processes. This layered origin would explain why no two XRGs are quite alike, and why even within this class, we find wide variation in wing length, brightness, curvature, and symmetry. But XRGs don't just help us understand galaxies. They also help us probe the nature of black holes themselves. One ongoing puzzle in astrophysics is whether black hole spins are mostly aligned with their host galaxies or randomly oriented. If most supermassive black holes spin in directions unrelated to their surrounding disks, that suggests a chaotic accretion history dominated by random inflows. But if spins are generally aligned, that points to more stable, long-term feeding from a well-formed disk. XRGs, by revealing past spin changes, offer a window into black hole angular momentum history, something few other observations can provide. As more XRGs are identified and studied in detail, we may begin to reconstruct spin evolution maps, diagrams that track how a black hole's spin vector changed over cosmic time. This could become one of the only direct empirical ways to test black hole spin alignment theories, which are otherwise notoriously difficult to confirm observationally. All of this makes the next generation of observatories particularly exciting. The Square Kilometer Array, SKA, for example, will not only allow us to detect thousands more XRGs, it will let us detect them fainter, smaller, and further away, potentially mapping their distribution across cosmic history. If we begin to see trends, such as more XRGs appearing in earlier epochs, it could tell us when black hole mergers were most common. That, in turn, could inform models of galaxy assembly, dark matter halo mergers, and even the formation timeline of large-scale cosmic structures. This brings us to an even broader implication: the connection between XRGs and the cosmic web. Massive galaxies often reside at the nodes of the cosmic web, the vast filamentary structure formed by dark matter, gas, and galaxies. These intersections are regions of high activity, mergers, gas inflow, and gravitational complexity. If XRGs are more likely to form in these hubs, it could mean that their formation is tied not just to local events, but to cosmological structure itself. In this view, XRGs become cosmic weather vanes, pointing not just to the motions within a galaxy, but to the flows and collisions of the universe's large-scale framework. What started as an odd pattern in a few radio images has now blossomed into one of the most interdisciplinary phenomena in modern astrophysics, connecting jet physics, black hole dynamics, galactic evolution, intergalactic environments, and cosmology. Each X-shaped radio galaxy is a story told in whispers, faint, distorted, ancient, but together they sing a larger song. A song of turbulence and transformation, of forgotten collisions and invisible forces. They are the ghosts of galactic pasts and the signals of unseen futures. And they're still only beginning to reveal their secrets. As we continue to unravel the enigma of X-shaped radio galaxies, we find ourselves venturing into deeper theoretical territory, where astrophysics borders philosophy. What do these galaxies really mean for our understanding of cosmic history? Why does nature seem to favor certain patterns, like symmetry, repetition, or sharp angular changes, in systems that operate on principles of chaos and randomness? The X shape is both elegant and startling, a stark cross carved across the cosmic void, whispering of dramatic pasts and violent transformations that remain unseen in any wavelength but radio. To understand just how extraordinary X-shaped radio galaxies, XRGs, are, consider the contrast with classical radio galaxies. In the simplest cases, these galaxies exhibit twin jets that stream out in nearly perfect opposition from a central black hole. These jets inflate lobes of relativistic plasma, which glow in the radio spectrum and form the iconic double lobe appearance. Over time, these jets can switch off, reignite, or wobble slightly, but their symmetry and direction are generally coherent. XRGs, by contrast, seem like rule breakers, messy, misaligned, and rebellious. Some researchers have begun thinking of XRGs not just as a type of radio galaxy, but as a time capsule of rare cosmic phenomena, events that may occur only under special circumstances, and only in specific environments. Their formation likely requires a Goldilocks scenario, a massive black hole, a supply of fuel, a prior merger, and a rich surrounding medium to record the lingering traces of past jet activity. That combination is uncommon, which may be why XRGs themselves are rare. Yet, as deeper surveys continue to probe the faint edges of the radio sky, that rarity may be more apparent than real. Instruments like LOFAR, Low Frequency Array, and the upcoming SKA are uncovering radio structures at much lower brightness levels than ever before. Already, LOFAR has revealed previously invisible lobes, halos, and wings in galaxies once thought to be simple or inactive. Many galaxies are now being reclassified as possible XRGs, their old wings brought into view by the sensitivity of modern telescopes. It raises the possibility that many radio galaxies go through an X-shaped phase, and we've simply been blind to it. If this is the case, then the X-shape may be a transitory phenomenon, a kind of jet adolescence, marking a period of upheaval and redirection. Just as stars go through unstable pre-main sequence phases or variable outbursts, galaxies too may have short-lived but energetically significant episodes that leave deep scars on their radio structure. In this interpretation, an XRG isn't a final state, it's a fleeting stage. And that makes catching one in the act all the more scientifically valuable. The behavior of these galaxies also provides a unique testing ground for magnetohydrodynamic (MHD) simulations. The flow of charged plasma in the presence of magnetic fields, over cosmic distances and under relativistic conditions, is one of the most complex problems in theoretical physics. The jets of active galactic nuclei, AGNs, especially those in XRGs, act as real-world laboratories for these phenomena. By modeling how jets are launched, how they propagate, and how they are deflected or redirected, researchers can refine the underlying equations that govern plasma physics. And there's another dimension to consider: polarization. Radio waves can be polarized, meaning the orientation of their electric field follows a specific direction. The polarization structure of radio lobes tells us about the magnetic field alignment within the plasma, and that in turn provides clues about the history and evolution of the jets. In XRGs, studying the polarization of the wings compared to the active lobes helps astronomers determine whether the wings are backflows, relics, or diverted streams. Early studies show distinct differences in polarization patterns between the wings and the active jets, supporting the idea that the wings are older, fainter, and shaped by different forces than the main lobes. This is where multi-wavelength studies become crucial. While XRGs are best seen in radio, they also have signatures in optical, infrared, and X-ray wavelengths. Optical images from telescopes like the Hubble Space Telescope reveal the structure of the host galaxy, often a massive elliptical with signs of tidal features or recent mergers. Infrared data, especially from instruments like the Spitzer Space Telescope or the James Webb Space Telescope, JWST, can uncover dusty star formation regions or hidden nuclear activity. And X-ray observations, particularly from the Chandra X-ray Observatory, show the hot gas halos that surround these galaxies, halos that can bend, compress, or scatter the jets, influencing their final shape. Taken together, these observations build a three-dimensional picture of an XRG's past. It's like reconstructing a crime scene from fragments. The faint wings are the footprints of a former suspect. The active lobes are the present action. The hot gas is the terrain that channeled or obstructed the escape. And the central black hole? It's both the criminal and the victim, a powerful force acting in a chaotic cosmos, shaped by and shaping the galaxy around it. XRGs also play a role in our understanding of feedback mechanisms in galaxy evolution. Black hole jets are not passive structures. They inject vast amounts of energy into their surroundings, heating gas, quenching star formation, and sometimes blowing entire cavities in galactic halos. In the so-called radio mode feedback, the jets from an AGN can prevent gas from cooling and collapsing into new stars. This helps explain why massive galaxies don't become even more massive through unchecked star formation. In XRGs, where jet direction has changed significantly over time, the feedback effect becomes even more complex. The old wings show that energy was once dumped in one direction, while the new jets now heat or displace gas elsewhere. This rotating influence may prevent cooling across a broader swath of the galaxy, making XRGs particularly efficient at quenching star formation. They are like rotating sprinklers of energy, denying cold gas the chance to coalesce into stars. Some simulations even suggest that such black hole feedback could regulate not just individual galaxies, but the thermal evolution of entire galaxy clusters. As we push further into this cosmic puzzle, researchers are now examining the alignment between the optical axes of the host galaxy and the radio wings. Interestingly, in many XRGs, the wings are aligned along the minor axis of the elliptical host galaxy. This suggests a deep link between the galaxy's stellar distribution and the formation of the wings, perhaps the gas density is lower along the minor axis, making it easier for backflows or redirected jets to expand in that direction. Others argue that this alignment supports the backflow model over the spin-flip model. But as with much in science, it could be both, multiple processes operating simultaneously. Then there's the question of jet precession. Some models posit that the black hole's spin axis slowly wobbles due to gravitational interactions with a second black hole, or due to accretion from a misaligned disk. If this precession is significant, it could cause the jets to sweep across different parts of the sky over millions of years, carving out structures that, when viewed in projection, form an X. Some XRGs show subtle curvature in their wings that hints at this slow drift, while others exhibit sharp transitions more consistent with a sudden spin flip. The diversity of shapes, therefore, reflects a diversity of formation pathways. And what about the cosmic timescale? Most radial lobes fade after a few tens of millions of years. So when we see both wings and lobes in an XRG, we're seeing a galaxy that underwent a major event not too long ago, cosmologically speaking. This makes XRGs cosmic timestamps, recording the moment when a galaxy's central engine shifted its alignment, reignited, or rebounded after a merger. Each one is a relic, not of a static universe, but of a dynamic cosmos in motion. This temporal aspect becomes even more significant when we consider the possible future of these galaxies. What happens after the X-shape fades? Do the jets stabilize? Does the black hole enter a dormant phase? Or does another merger reboot the cycle, and the process repeats? New jets, new lobes, new wings? If so, some galaxies might eventually become multi-X shaped, their histories layered like geological strata. Already, a few candidates have been found with more than 2 lobes or unusual nested structures, perhaps the galactic equivalents of Russian nesting dolls, each layer a testament to a past life. The implications extend beyond astronomy. As we decipher the hidden story of X-shaped radio galaxies, we confront some of the most profound questions in science. How do galaxies grow and evolve? How do black holes influence the universe around them? Can a single object's radio shape reveal a billion years of cosmic drama? The answer, increasingly, is yes. And so, as we move even further into the intricacies of X-shaped radio galaxies, the universe continues to reveal layers of complexity that transform these peculiar objects from obscure curiosities into profound cosmic landmarks. Each X-shaped galaxy is like a frozen scream from deep time, a silent signature of an event so energetic and so colossal that even light waves across millions of light years cannot carry all its meaning. To grasp the full impact of such galaxies, we must not only look at them as snapshots but as narratives, ongoing stories unfolding on unimaginable timescales. These galaxies also sit at the intersection of multiple fields of astrophysics. Their formation touches on galactic mergers, black hole physics, relativistic jets, plasma dynamics, magnetism, and cosmological structure formation. Few astronomical objects act as such a melting pot of physical phenomena. And yet, despite their seeming rarity and mystery, X-shaped radio galaxies might represent a natural and repeatable stage in the evolutionary track of the most massive galaxies in the universe. One of the most compelling aspects of studying these systems is the possibility that they hold the key to detecting the gravitational wave footprints of past black hole mergers. While gravitational waves themselves are fleeting, the astrophysical consequences of black hole coalescence are not. A merger can lead to a recoil kick, where the newly formed black hole is ejected slightly or shifted within the galactic core. This sudden movement could destabilize the accretion disk, cause a flip in spin alignment, or prompt a complete reorientation of the jet axis, all of which could result in the X-shaped pattern we see today. And so, even though LIGO and other gravitational wave detectors are only sensitive to current mergers, XRGs may serve as fossilized evidence of those long-past gravitational wave events. The wings may quite literally be the silent aftermath of titanic collisions that once shook spacetime itself. This turns every XRG into a sort of cosmic crime scene, where we can study the debris of a gravitational battle that occurred millions or even billions of years ago. Another dimension worth exploring is the environmental impact of XRGs on their cosmic neighborhoods. We've already touched on how jets can suppress star formation, but the wings themselves, especially if formed by backflows or deflected plasma, can also energize the surrounding intergalactic medium, IGM. This extended heating may affect not just the host galaxy, but also nearby dwarf galaxies, intracluster gas, and even cosmic filaments. Over time, such energetic outflows might reshape entire galactic ecosystems, playing a quiet but persistent role in cosmic evolution. In fact, there's a growing hypothesis that AGN feedback, especially in powerful, morphologically complex systems like XRGs, is critical for maintaining the structure of the cosmic web. If galaxies like these inject heat and turbulence into the filaments connecting clusters, they might slow down gas accretion, suppress excessive structure formation, and even contribute to the uniformity of the cosmic microwave background, CMB, in indirect ways. But there is another, more speculative frontier emerging in discussions around X-shaped radio galaxies, the idea that they might be gateways to new physics. Some researchers have proposed that unusual jet alignments, especially abrupt changes in direction, could be triggered not just by black hole mergers, but by interactions with dark matter substructure. If the host galaxy passed through a region with a dense clump of dark matter, an invisible, massive object, its gravitational influence could distort or deflect the inner part of the AGN's accretion disk. This might result in a temporary jet misalignment, a redirection of the energy flow, or even an off-axis lobe that later appears as one arm of the X. Of course, this is speculative, but that's the nature of frontier science. As our observational power grows, so too must our theoretical imagination. X-shaped galaxies remind us that not everything in the cosmos follows clean, linear rules, and that outliers often carry the most information. Indeed, the rarity of XRGs might not be a limitation, but a clue. If they were common, we'd dismiss them as a routine step in radio galaxy evolution. But their very strangeness is what demands attention. In science, outliers are often the gateway to discovery, the peculiar data points that don't fit the model, the noise that turns out to be signal. In the same way that the orbit of Mercury hinted at general relativity, or that the bending of starlight predicted gravitational lensing, the unexpected structure of XRGs may foreshadow a deeper understanding of gravity, space-time, and cosmic flow. There are also cultural and philosophical implications to consider. When we think of galaxies, we often picture elegant spirals or spherical ellipticals, icons of balance and stability. But X-shaped radio galaxies show us a universe that is more violent, chaotic, and dynamic than we might prefer. They are symbols of cosmic trauma, of galaxies ripped apart, of black holes recoiling through space, of jets redirected in fury. And yet, out of this violence comes symmetry. Out of chaos comes structure. The X-shape, in all its strangeness, is a cosmic mandala, a moment of balance forged through titanic upheaval. We cannot help but feel humbled by this. Light from these galaxies has been traveling for hundreds of millions of years to reach us. In many cases, the events that formed their wings occurred before life on Earth even began. And yet, here we are, decoding their story, pixel by pixel, photon by photon, from telescopes planted on a tiny rock orbiting an ordinary star. That's the true power of astronomy. It lets us glimpse the ancient and the immense, the terrifying and the beautiful, and it reminds us that we are a part of this story, not separate from it. We are made of the same elements as these galaxies, shaped by the same physics, and moving through the same universe. When we study X-shaped radio galaxies, we aren't just peering into a strange corner of the cosmos. We're looking into the echo of our own cosmic origin. And perhaps that is the deepest mystery of all. That something as simple as an X in the sky could carry within it the secrets of black holes, the memory of galactic collisions, the record of gravitational waves, the shape of dark matter, and even the evolution of everything we know. We've only begun to scratch the surface. Despite the progress we've made in understanding X-shaped radio galaxies, many essential questions remain unanswered. Questions that probe not only the structure of these galaxies but also the underlying framework of the universe itself. The deeper we peer into the nature of these formations, the more it becomes evident that they may represent more than just astrophysical anomalies. They might instead be the visible remnants of hidden dynamics, forces that are not easily explained by classical models alone. One such force could involve cosmic magnetic fields, which remain one of the least understood aspects of astrophysics. The universe is threaded with magnetic fields, from planets and stars to galaxies and even the cosmic voids themselves. In XRGs, magnetic fields could play a decisive role in shaping the jets and wings. For instance, the interplay between the black hole's spin and the orientation of the magnetic fields in the surrounding accretion disk could result in the dramatic reorientation of jet structures. These cosmic magnetic fields, especially when compressed or twisted during galaxy mergers or rapid black hole spin realignment, might store and release vast amounts of energy. In such a scenario, the radial wings wouldn't merely be passive trails of past jets. They might be magnetized outflows, where synchrotron radiation continues for eons, powered by lingering magnetic turbulence. This raises the possibility that the wings themselves are not just remnants, but still active structures, slowly dissipating energy long after their central jets have shifted course. This idea becomes even more fascinating when you consider how these wings can span hundreds of thousands of light years, vastly outscaling the visible optical components of their host galaxies. Imagine a galactic nucleus no bigger than a tiny smudge of light, launching jets that carve patterns into the cosmic medium stretching across distances beyond our solar system's comprehension. What other types of cosmic patterns could be hidden in this radio noise, waiting to be uncovered? We must also address another curious dimension, the symmetry of the X-shape. While many XRGs appear symmetrical, showing fairly equal and opposing wings, some are lopsided, skewed, or curved. These deviations from perfect symmetry might be the fingerprints of subtle cosmic imbalances. Perhaps one side of the jet passed through denser intergalactic material, slowing it down or deflecting it. Perhaps an off-center black hole, or a delayed merger caused an asymmetrical spin flip. Or perhaps some invisible force, dark matter substructure, intergalactic currents, or ancient remnants of cosmic inflation, nudged the flow just enough to tip the balance. In fact, one underexplored idea is that these asymmetries might be used as cosmic compasses. If we could analyze enough X-shaped galaxies, map their asymmetries, and compare them to the large-scale structure of the universe, we might discover correlations, traces of how galaxies interact with the cosmic web itself. Their shapes could then become cosmic flow tracers, pointing in the direction of gravitational gradients or hidden mass concentrations. What's even more astounding is that these distant radio galaxies may also teach us something about the future of our own Milky Way. At some point in the next few billion years, the Milky Way is expected to collide and merge with the Andromeda Galaxy. That cataclysmic event will transform both galaxies, possibly awakening dormant supermassive black holes and initiating intense episodes of star formation, jet activity, and galactic realignment. If our central black hole becomes active, perhaps forming jets in response to an accretion frenzy, it is not unthinkable that our post-merger galaxy could produce a similar signature to an XRG. Imagine a distant civilization, billions of years from now, looking at the remnant of what was once the Milky Way and seeing an X-shaped radio galaxy stretching across space, a ghostly echo of a collision that occurred long before their species evolved. Just as we now interpret the meaning of these strange cosmic structures, so too might others, long after we are gone. Returning to the observational side, a growing challenge, an opportunity, is the rise of next-generation telescopes. The Square Kilometre Array, SKA, one of the most ambitious radio astronomy projects in human history, promises to detect tens of millions of radio galaxies, including faint or distant XRGs that current surveys can't resolve. With its unprecedented sensitivity and angular resolution, the SKA may uncover entire populations of faint, high redshift X-shaped galaxies, giving us the first statistical sample large enough to truly study their evolution across cosmic time. Complementing that will be data from instruments like the James Webb Space Telescope, JWST, which, while not a radio telescope, can observe the infrared signatures of the stars and dust in XRG host galaxies. Combining this with X-ray data from Chandra and other observatories will create multi-wavelength maps of these galaxies, allowing us to piece together not just their structure but their history, how and when their jets switched, how their black holes evolved, and how their host galaxies responded. But with this flood of data will come new mysteries. Already, astronomers are noticing what may be intermediate forms of X-shaped galaxies, systems that don't quite display the classic X shape, but show hints of wing-like extensions or disrupted lobes. Could these be proto-XRGs, caught in the act of transformation? Or are they failed XRGs, where conditions were right for jet reorientation but not powerful enough to leave lasting wings? Even more intriguingly, there are some galaxies that appear to have multiple sets of wings, forming more complex, hourglass or butterfly-shaped structures. These suggest repeated jet reorientation events, possibly due to multiple mergers over time. Each set of wings could represent an entire era in the life of the galaxy, a black hole's shifting gaze across eons. And then there's the haunting possibility that some XRGs may have formed through processes we don't even understand yet. What if their symmetry isn't just a physical consequence, but a deeper pattern related to the geometry of spacetime itself? Some theoretical physicists have speculated about the role of cosmic strings, hypothetical topological defects from the early universe that could interact with matter in exotic ways. Could a cosmic string encounter with a galaxy cause a sudden jet reorientation, or even split the plasma into multiple paths? It's a long shot, to be sure. But then again, so was the idea of gravitational waves, until we built detectors sensitive enough to hear them whisper through the Earth. Science has a history of turning wild theories into accepted knowledge once the tools are built and the data starts pouring in. Ultimately, the study of X-shaped radio galaxies invites us to embrace the tension between mystery and method, between what we can explain and what we are still only beginning to guess. They are silent testimonies to cosmic upheaval, reminders that the universe does not evolve in straight lines but in spirals, flips, collisions, and echoes. As we reach the far edges of this exploration, we are reminded that every answer in astronomy leads to deeper questions. Why do some galaxies switch jets and others don't? What determines the shape, duration, and energy of the wings? How do we trace a chain of events across hundreds of millions of years using only light and magnetism? What forces in the universe are invisible, yet leave behind signatures so vast and symmetric that they span hundreds of thousands of light years? These questions aren't just academic. They are existential. They ask us to place ourselves in the context of a universe that is not only older than we can imagine, but far more complex than we dare to believe. And still, it speaks. Through the language of light. Through the silence of radio waves. Through shapes that defy simplicity. Through excess that mark the spots. Yet, as we follow the trail of these cosmic excess deeper into the abyss of astronomical data and theory, we begin to suspect that X-shaped radio galaxies might represent only the surface expression of far more intricate galactic mechanics. Much like how a whirlpool on the ocean's surface hints at currents far below, the distinctive patterns in these galaxies might be mere hints, echoes, of multidimensional physics playing out over billions of years. To understand just how deep this complexity runs, consider how rare X-shaped radio galaxies are compared to other types of radio galaxies. Their very rarity forces astronomers to ask, are we catching these objects in a brief transitional phase, or are the conditions required for their formation exceptionally precise? If jet reorientation or black hole spin-flip events are relatively common, then why aren't XRGs more widespread? The answer may lie in the idea of selective visibility. That is, many XRGs may exist, but the wings might fade over time, or be oriented in such a way that from our vantage point, they don't form an obvious X. This introduces the concept of observational bias in astronomy. What we see isn't always what exists, it's what we're able to detect based on light, angle, distance, frequency, and available technology. For instance, if the wings of an XRG are aligned close to our line of sight, they might blend into the main jets, appearing as just a brighter central source rather than an extended X. Conversely, if the wings are composed of lower-energy electrons, their radio signal might fall below detection thresholds, especially in older systems. In this light, the X-shaped galaxies we do observe might be just the brightest, youngest, or best-oriented examples of a phenomenon that's far more common but usually hidden from us. In fact, with AI-assisted analysis and advanced sky surveys like LOFER and Meerkat generating petabytes of radio data, researchers are beginning to discover more candidate XRGs, some of which don't match classical definitions but instead show partial wings, twisted lobes, or warped jets. These XRG-like sources may represent different stages in the life cycle, or completely new classes of jet dynamics. And that's where the discussion begins to touch something profound: the life cycles of galaxies themselves. Just like stars, galaxies have birth, growth, interaction, and death. XRGs, with their unmistakable markings, might be the scar tissue left behind after a galaxy has undergone major upheaval, a kind of cosmic trauma signature. Each wing might represent an era, a battle, a transformation. They are visual artifacts of gravitational violence that once tore through the very heart of the system. This brings us to a striking parallel with human forensics. Imagine walking into a room after a dramatic event has occurred. The furniture is overturned, a window shattered, and strange patterns are scorched into the walls. You don't know what happened, but the evidence tells a story. That's what X-shaped radio galaxies are to the astronomer. They are the aftereffects of events that we didn't witness, but that left unmistakable traces written in plasma and magnetic fields. Sometimes those stories are clearly linked to a galaxy merger, when two galaxies collide and their central supermassive black holes eventually coalesce. Such a collision might disturb the orientation of the resulting black hole, shifting its spin axis and causing the jet direction to change dramatically. The original jets fade into wings, and the new jets take over, forming the X. But in other cases, the cause is more ambiguous. There are galaxies with X-shaped radial lobes but no nearby merging partner, no obvious signs of tidal disturbance. Could this mean there are internal mechanisms, perhaps instabilities in the accretion disk, or sudden shifts in the balance between inflowing gas and magnetic pressure, that could also reorient jets without the need for mergers? Or could it point to even stranger phenomena, such as frame dragging on cosmic scales? According to general relativity, rotating massive objects drag spacetime around them, a phenomenon known as the lens stirring effect. If supermassive black holes rotate fast enough, their spin could twist nearby space, causing the inner accretion disk to wobble and precess. Over time, this precession could alter the jet direction, especially if it's sustained or suddenly intensified. That might lead to a slow or even abrupt jet flip, and possibly the formation of X-shaped radial lobes. But if that's the case, what determines whether a galaxy gets one set of wings or multiple? Could some XRGs have changed jet orientation more than once? Might there be Z-shaped radial galaxies, or even more intricate morphologies, that represent higher-order symmetries or repeated transformations? The answer is yes. Astronomers have, in fact, cataloged some galaxies that appear to have multiple reorientation events, where the jet path is not just an X but more like a knot, a tangle of ancient radial lobes, each pointing in a different direction, each telling a different part of the galaxy's story. And if we think of black holes as engines, then we must ask, what causes an engine to change its exhaust direction? Is it merely an external force, like a merger or an accretion instability, or is it something self-generated, a kind of feedback loop? In many active galaxies, jets themselves interact with their surroundings, inflating huge cavities in the intergalactic medium. These cavities, radio bubbles, can disrupt future inflows of gas, altering the conditions under which the black hole accretes mass. In this way, the jet is indirectly sculpting its own future. The idea is recursive, like a pen that changes its writing style based on the paper it's written on. And herein lies a deeper philosophical parallel. X-shaped radio galaxies could be seen as a cosmic metaphor for feedback, a system that changes based on its own past, looping through cycles of cause and effect, action and reaction. This recursive nature touches on a fundamental principle found across physics, biology, and even psychology. Systems evolve not just in a forward linear path, but in responsive loops, where past states inform the future. This concept is strikingly echoed in the structure of time itself. Some physicists speculate about closed time-like curves, theoretical paths through spacetime where the future loops back into the past. While such ideas are still speculative, the symmetry and recursive qualities of XRGs invite us to ponder whether the universe expresses itself through patterns of echo, symmetry, and reversal far more often than we expect. Even on a more grounded level, the idea that XRGs may store a chronology of galactic events in their structure is incredibly exciting. Just like tree rings reveal years of growth or ice cores preserve records of ancient climates, the orientation, brightness, and length of each wing and jet in an XRG may preserve a timeline. By examining the aging of radio lobes, scientists can estimate how long ago each jet was active. This creates the possibility of reconstructing a timeline of black hole activity over tens or hundreds of millions of years. One could imagine a future in which astronomers routinely read these timelines, extracting the histories of hundreds of thousands of galaxies, comparing them across the universe to search for global patterns, moments when many galaxies change jet direction at once. Could such coordinated reorientations point to cosmic scale influences, like gravitational waves from distant mergers, or large-scale structure collisions that ripple through clusters of galaxies? This idea is speculative, but not impossible. Already, large-scale structures like galactic filaments, voids, and walls are known to influence galaxy motion and orientation. If a galaxy cluster moves through a cosmic filament, the inflow of matter could affect jet directionality. Over time, these flows might create aligned structures, rows of galaxies with similarly shaped radio jets or wings, aligned not randomly, but shaped by the underlying architecture of the universe. In this sense, X-shaped radio galaxies could act as markers, not just of internal galactic dynamics, but of the cosmic scaffolding itself. They are not merely passive relics, but active participants in a dialogue that spans hundreds of millions of light years and billions of years. They are maps, stories, evidence, warnings, and invitations. They are invitations to decode the hidden grammar of the cosmos, an ancient script written in radio waves, electric fields, magnetic tension, and gravitational distortion. X-shaped radio galaxies aren't just scientific curiosities. They're keys to unlocking fundamental questions about the behavior of matter and energy under extreme conditions. They whisper of collisions so powerful they ripple the very fabric of spacetime, and tell of black holes that lurch and spin like titans across the galactic core. Each one may harbor not only a tale of cosmic violence, but of recovery and transformation, where a galaxy forges a new identity from the remnants of its own upheaval. But as we attempt to decipher this galactic script, we're also confronted with something profound and humbling: our limitations as observers. Despite our increasingly sensitive instruments, we're still bound by light travel time, perspective bias, and the fundamental constraints of observational astronomy. The wings of many X-shaped galaxies may have already faded from detectability, their stories cut off mid-sentence. Others might only now be beginning their transition, as their central jets shift direction and start to etch new signatures into the sky, signatures that we may not see for millions of years. Even more intriguing is the thought that these colossal structures might be shaping their local environments in ways we barely understand. As jets carve through intergalactic space, they don't move through a vacuum. They plow through tenuous gas, stir magnetic fields, compress clouds, and may even trigger new star formation or suppress it entirely. The relic wings, those secondary, off-axis lobes, aren't just passive leftovers. They too interact with the intergalactic medium, stirring turbulence and pushing matter that could later coalesce into stars, planets, or even life. The ripple effects of an X-shaped radio galaxy might seed or stunt entire galactic lifetimes. The scale of influence here is staggering. Picture a single black hole at the center of a galaxy. It's no larger than our solar system, yet it commands jets that span hundreds of thousands of light years. These jets in turn sculpt matter across millions of light years. Now multiply that by the tens of thousands of known radio galaxies and the vast unseen population we've yet to detect. The result is a portrait of a universe being constantly rewritten by titanic, relativistic quills driven by spinning singularities, each shaping its corner of the cosmos with ink made of plasma and radiation. And still, the true cause of the X-shape remains elusive. Is it always a jet reorientation? Is it a backflow caught in a uniquely aligned gravitational field? Or is there a more exotic explanation, perhaps involving dark matter halos exerting asymmetric gravitational forces that divert plasma flow in unexpected ways? If dark matter halos are triaxial rather than spherical, as some models suggest, they could channel jet backflows preferentially along one axis. This might account for the shape of the wings in a way that doesn't require a dramatic jet reorientation. That would mean the X shape is not a sign of violence, but of invisible structure, an unseen hand sculpting visible features. This hypothesis brings XRGs into contact with another vast cosmic mystery, dark matter. If their wings are shaped by the hidden contours of dark halos, then mapping them precisely might allow astronomers to reverse engineer the mass distribution in galaxies. Each X-shaped structure might become a probe, a gravitational sonar returning echoes from the darkness that surrounds and permeates every galaxy. It's not science fiction, it's testable physics. With precise radio observations and models of plasma dynamics, the faint glow of ancient jets could illuminate the architecture of the invisible. There are even more radical ideas. Some researchers have speculated that jet realignment in XRGs could be caused by interaction with hypothetical cosmic strings, infinitesimal but immensely dense relics from the early universe. If one were to pass through a galaxy, the gravitational wave burst could jolt the central black hole enough to change its spin axis. While such an event is incredibly speculative and rare, the theoretical framework is not entirely ruled out by physics. In that sense, every mysterious morphology in the sky is a puzzle piece that might one day fit into a theory of everything. And if we zoom out from one XRG to many, a larger picture emerges, a cosmographic atlas of these peculiar objects across the universe. Their distribution, frequency, and orientation could be plotted and analyzed for patterns that go beyond individual galaxies. Do more XRGs occur in certain types of galaxy clusters? Are they more frequent in earlier cosmic epochs? Do their axes align with the filaments of the cosmic web, suggesting a deeper structural coherence to their orientation? These are not idle questions. They are active areas of investigation in modern astrophysics. As radio telescopes like LOFAR, the Square Kilometer Array, SKA, and others continue to scan deeper into the universe, the catalog of X-shaped galaxies is growing. But these aren't just new entries in a database. Each one is a Rosetta Stone waiting to be decoded. We don't yet have the full language. Our vocabulary of jet mechanics, gravitational dynamics, and magnetic field evolution is still growing, but every observation brings us closer to fluency. And here's where we must also marvel at the human element of this search. These discoveries are not made solely by machines but by people, astronomers, physicists, data analysts, and citizen scientists alike, who spend years poring over faint smudges in radio maps, drawing connections between abstract concepts, running simulations on supercomputers, and refining theories that bridge the realms of the known and the speculative. Some of the most important insights into XRGs have come not from single, eureka, moments, but from decades of collaborative work, matching radio emissions to optical images, comparing jet angles to galactic morphology, reconciling theory with stubborn data. It's a long and meticulous process, one that stretches across institutions, countries, and generations. And it reminds us that the pursuit of cosmic truth is not only about uncovering what is out there, it's also about refining who we are as thinkers and explorers. In the presence of an X-shaped galaxy, we are both detectives and poets. We dissect its structure with algorithms and models, but we also gaze at its symmetry with awe. We see in it the fingerprints of titanic forces, and perhaps something of ourselves. For we, too, are shaped by invisible dynamics, by collisions and transformations, by forces we often barely understand. In a sense, we are not unlike galaxies, carrying scars from past interactions, radiating energy in new directions, forever navigating the tension between chaos and order. So the next time you look up at the night sky and think about galaxies billions of light years away, remember, some of them are marked by colossal, invisible battles. Some of them wear their history in giant glowing scars that stretch for hundreds of thousands of light years in an unmistakable X. They are not random. They are not simple. They are stories written in the oldest language of all, the language of light and motion and time. And those stories are still being told. Yet, for all we've uncovered, we are only just beginning to grasp the full implications of what X-shaped radio galaxies, XRGs, might reveal, not only about the galaxies themselves but about the cosmic landscape that surrounds them. The peculiar X-shape is not a trivial aesthetic anomaly. It is a clue embedded in space-time, a marker of dynamic evolution, and possibly even a cipher for decoding hidden universal laws. There's a deep irony at play here. While these colossal structures are detectable across unimaginable distances, the very process that gives rise to them may take place within a few light hours or even light minutes of the supermassive black hole at their centers. This mismatch of scale, the central engine's minuscule size versus the colossal size of the resulting radio lobes, underscores how powerful and finely balanced the mechanisms must be. A slight tilt in the spin axis, a minor accretion event, or a black hole's recoil by a few kilometers per second can set into motion a series of consequences that alter a galaxy's architecture over millions of years. It's also important to acknowledge that the very existence of XRGs challenges the uniformity we once assumed about radio galaxies. For decades, astronomers believed in a relatively tidy classification system. You had FRI and FR2 galaxies, categorized by their radio brightness distribution and morphology. But X-shaped galaxies don't fit neatly into either of those bins. Many exhibit hybrid characteristics. Their central jets might resemble one category while their wings defy it entirely. This prompts us to rethink how we categorize celestial phenomena and pushes us toward more fluid, multidimensional classification systems that account for evolutionary history, environment, orientation, and time. Orientation, especially, plays a deceptive role. Because we're confined to a single vantage point on Earth, or at best, within the inner solar system, we see only two-dimensional projections of these three-dimensional cosmic structures. A truly X-shaped radio galaxy might not look like an X at all from a different angle. It might resemble a T, a V, or even a straight line. This observational bias reminds us that part of understanding these systems involves mentally rotating them, modeling them, and seeing them from perspectives we can never physically occupy. Simulations become crucial tools in this regard, allowing us to reconstruct plausible geometries and dynamic histories from limited data. Furthermore, time introduces another layer of distortion. What we see today is not what is happening now, but what happened millions or even billions of years ago. We're watching ancient light, fossil radiation from dead jets and dormant lobes. A radio lobe we observe today may have ceased being active when dinosaurs roamed the Earth, or long before. It's like looking at a paused movie and trying to infer the plot from a single frame. And yet, with enough of these frames, these XRGs across space, we begin to glimpse patterns, rhythms, cycles. In fact, the idea of cyclic activity in radio galaxies has gained significant traction. Some XRGs may not be the result of sudden events, but of oscillating activity. Jets might periodically shut down and reignite, each time possibly aligning in a slightly different direction due to instability in the accretion disk or black hole spin. Over millions of years, these cycles could produce multiple sets of lobes, like tree rings or seismic strata, each set hinting at a different phase of galactic life. The wings of XRGs, in this view, might not just be passive leftovers from a single past event, but evidence of a repeating heartbeat in the life of an active galactic nucleus. This introduces a tantalizing question: could all radio galaxies go through an X-shaped phase at some point in their evolution? Maybe what we see as a rare subclass is actually a temporary state in a broader dynamic process. If so, our current classification schemes are merely capturing snapshots in an ongoing transformation. This would mean XRGs aren't outliers. They're moments of transition, of upheaval, of change. And what might trigger those changes? Beyond galactic mergers and black hole realignments, some researchers suggest magnetohydrodynamic instabilities, essentially, turbulence in the plasma flow itself. Over vast distances, even slight asymmetries in pressure, magnetic tension, or external gas density could cause jets to bend, stall, or split. Such interactions could explain why some XRGs have wings that are sharp and narrow, while others are diffuse and wide. The environment matters. A galaxy embedded in a dense cluster might experience very different feedback mechanisms than one drifting through a void. The way the jets push against the surrounding medium could radically affect their morphology and longevity. In that sense, XRGs become not just indicators of internal galactic dynamics but probes of cosmic environments. By analyzing the properties of the wings, their brightness, symmetry, polarization, and spectral index, we can infer the density and temperature of the medium they expanded into. This transforms these galaxies into tools of intergalactic cartography. Just as seismologists use the echoes of earthquakes to map the Earth's interior, astronomers can use the fossil jets of radio galaxies to map the structure of the cosmic web. This turns XRGs into more than cosmic mysteries. They become instruments. Instruments that allow us to study the distribution of baryonic and non-baryonic matter in the universe. Instruments that might one day help constrain models of dark energy by revealing how cosmic structures evolved over time. Instruments that reach back through time, through space, and through layers of theory to touch the very foundations of cosmology. And perhaps most astonishingly, we're not limited to passive observation. We're entering an era where we can manipulate and cross-correlate massive datasets using machine learning to identify hidden patterns in XRG morphology and distribution. These methods can spot anomalies or recurring themes that human eyes might miss. Artificial intelligence has already begun uncovering rare double-lobed or hybrid galaxies that were buried in survey archives, overlooked because their shapes didn't match predefined categories. The future may bring neural networks that can predict an XRG's origin story from its radio fingerprint alone. And this future is arriving fast. With next-generation instruments like the SKA, we'll soon be able to detect radio galaxies an order of magnitude fainter and farther than ever before. We might discover thousands or millions of XRGs, each bearing a unique signature. Some will reinforce existing theories. Others will shatter them. But together, they'll rewrite our understanding of how energy moves through the universe, and how galaxies evolve under the pressure of their own central engines. Imagine looking out across a sea of data, every point a beacon from a galaxy that once blazed with radiation, sculpted by jets that could tear through stars. The sky will look different, not static and serene, but alive and dynamic, full of scars and echoes, like a battlefield long after the fighting has ended. And at the heart of many of those beacons, we will find X-shapes, remnants of rotation, memory, and upheaval. They are not accidents. They are not noise. They are cosmic testimonies. And our job is to listen. As we continue to explore the deeper implications of X-shaped radio galaxies, one cannot help but consider the almost poetic nature of their existence. They are, in essence, celestial palimpsests, galactic manuscripts overwritten time and again by the hand of gravity, motion, and magnetic force. Just as ancient texts were inscribed and then erased, only to be written upon again, these galaxies show layers of their own histories, each jet and wing a line in the story of cosmic violence and rebirth. And this story isn't confined to a handful of anomalies in the sky. If X-shaped radio galaxies are indeed transitional phases, or evidence of episodic activity, then they represent a broader principle of cosmic evolution, that nothing in the universe is static. Every black hole spins, precesses, merges, or reorients, and each event sends ripples not just in gravitational waves but in vast outflows of matter and energy that shape entire galaxies. These X-shapes might be the punctuation marks in that sentence, periods, commas, or exclamations in the language of astrophysics. But the puzzle remains incomplete. Despite advances in simulations, surveys, and theory, no single explanation has yet accounted for every observed XRG. Some have wings with similar spectral ages to the active lobes, suggesting they were formed nearly simultaneously, supporting models of jet precession or backflow. Others show wings much older than the current lobes, pointing to a restarted jet scenario after a significant pause. A few defy expectations altogether: asymmetric X-shapes, triple-lobed galaxies, or even those with one wing appearing to spiral. These outliers push the envelope and compel theorists to revise or hybridize models. One particularly provocative idea is that gravitational wave recoil, a phenomenon predicted in general relativity, may be responsible for some of the most extreme XRGs. When two supermassive black holes merge, they can emit gravitational waves asymmetrically, effectively giving the remnant black hole a kick. This recoil can send the black hole careening through the galaxy at speeds of thousands of kilometers per second. If it continues to emit jets during this flight, the orientation shift would be extreme, potentially creating one of the sharpest and most dramatic X-shapes imaginable. Though such scenarios are rare, they are not impossible, and may be supported by radio galaxies that appear to have offset cores or disjointed jet axes. The interplay of jets and the intergalactic medium also introduces complexity. As jets propagate outward, they encounter resistance, interstellar gas, magnetic fields, and even the dark matter halo that subtly but significantly tugs on everything. In denser environments, backflow is more likely to be channeled and shaped into coherent wings. In sparser regions, the wings may be diffuse or absent altogether. So the morphology of an XRG might encode information not just about the black hole's behavior, but about the cosmic neighborhood in which it resides. Understanding that neighborhood requires a multi-wavelength approach. While radio observations map the lobes, X-ray data from observatories like Chandra can reveal the surrounding hot gas, and infrared surveys can expose obscured star formation in the host galaxy. Optical spectra, too, offer insights, tracing the velocity and composition of gas near the galactic core, or identifying signatures of past mergers. It's only by layering these observational domains, radio, X-ray, optical, infrared, that we get a complete picture. And then there's the question of feedback. XRGs are not passive relics. Their jets can suppress or trigger star formation. As relativistic particles plow through gas clouds, they heat them, stir them, sometimes expel them from the galaxy altogether. This feedback affects the evolution of galaxies and even entire clusters. Some simulations suggest that galaxies might experience several feedback episodes, each potentially linked to a different jet phase, and each possibly creating another set of wings. So, an X-shaped radio galaxy isn't just an aesthetic oddity, it's a driver of galactic destiny. From a theoretical standpoint, the hydrodynamics of jet formation are still being refined. How does a jet remain collimated across hundreds of thousands of light years? What initiates the sudden shift in direction seen in some XRGs? Magnetohydrodynamic, MHD, simulations are helping illuminate these questions, showing how magnetic fields can stabilize or disrupt jet flows, how disk instabilities can ripple upward to affect jet orientation, and how even slight anisotropies in the surrounding medium can deflect or sculpt radio lobes. It's a complex ballet of physics, plasma behavior, general relativity, galactic dynamics, and cosmic structure, all choreographed around a single, spinning, invisible point, the supermassive black hole. We often imagine black holes as the ends of things, but X-shaped radio galaxies remind us they are also engines of creation, shaping the very matter and energy of the universe across vast distances and timescales. In contemplating these structures, we're also reminded of our own scale in the universe. The wings of an XRG can extend over 1 million light-years, dwarfing our entire galaxy. The processes that shape them unfold over tens or hundreds of millions of years, far longer than any human civilization. Yet here we are, barely a century into radio astronomy, and already we're decoding these vast glyphs etched into the cosmos. What else might they tell us? Some researchers are even entertaining the possibility that studying XRGs could indirectly test aspects of quantum gravity or probe the distribution of dark matter in galactic halos. Because jets interact with everything they encounter, they may offer indirect evidence of otherwise invisible forces or particles. The way a jet bends, stalls, or diffuses could hint at properties of dark matter that gravitational lensing alone cannot reveal. There's also a philosophical resonance here. These X-shaped galaxies are cosmic crossroads, where past activity intersects with present motion, where ancient jets cross new ones, where the memory of a previous orientation lingers in the structure of the universe. They are, in a way, time made visible. And so the next time you look at a deep radio image, filled with odd shapes and asymmetrical lobes, remember, you're not just seeing light. You're seeing history, recorded in plasma, shaped by gravity, illuminated by the afterglow of cosmic upheaval. And at the heart of some of the most mysterious among them, you'll find the indelible shape of an X. But even the symbolic X shape that marks these galaxies is not a fixed signature. It varies, sometimes subtly, sometimes dramatically. Some X-shaped radio galaxies are faint and wide, like gentle brushstrokes across the cosmos. Others are sharp and angular, like cosmic scars. Some show a symmetric cross, others lean to one side. There are wings that are barely perceptible, like ghostly echoes of energy long since dissipated, and others so bright they rival the main jets in intensity. This diversity points to the multifaceted nature of their formation mechanisms. No single story, but a constellation of causes, overlapping and intertwining. And this brings us to the very frontier of observational astronomy. Upcoming and current generation telescopes are radically reshaping our view of these celestial structures. Instruments like the Square Kilometre Array, SKA, the Low Frequency Array, LOFAR, and the Meerkat Radio Telescope are pushing the limits of sensitivity and resolution. Where earlier surveys identified dozens of XRGs, these new arrays may uncover thousands, including those too faint or too distant to be seen before. We may find transitional forms, hybrid morphologies, or galaxies so bizarre they don't fit into any current framework. What's even more exciting is that these instruments allow us to see earlier in the universe's history. Most known XRGs are relatively local in cosmological terms, within a redshift range of about 0.1 to 0.5. But as we peer further back in time, we may discover X-shaped galaxies at higher redshifts, galaxies formed just a few billion years after the Big Bang. These would provide critical insights into how quickly supermassive black holes began to interact, merge, and reshape their environments. Imagine finding an X-shaped radio galaxy from the early universe, its wings stretching across intergalactic voids that had only recently coalesced. It would imply that the processes driving jet reorientation or black hole spin flips were already underway shortly after galaxy formation began. Such a discovery would force a reconsideration of cosmic timelines and the evolution of large-scale structure. Equally significant is the role of artificial intelligence in analyzing this growing mountain of data. Manually identifying XRGs from thousands of radio images is time-consuming and prone to human error. But machine learning algorithms, trained on known examples, can rapidly scan datasets and flag potential candidates, some of which may be too subtle or unconventional to be noticed by the human eye. These AI systems don't just recognize patterns, they learn what makes a galaxy exceptional. As algorithms become more sophisticated, they may even detect entirely new classes of radio galaxies, perhaps structures beyond the X-shape, indicating even more exotic physical scenarios. Could there be triple-flipped galaxies? Spiral-winged sources? Or galaxies with jets that corkscrew through space like spiraling lighthouses? It's within the realm of possibility, and in some cases, early hints of such forms have already been spotted. We should also consider the implications for galaxy classification. For decades, we've relied on the Hubble sequence, a system based on the visual appearance of galaxies in optical light, spirals, ellipticals, lenticulars. But XRGs challenge the idea that a galaxy's visible structure is its most important feature. In radio wavelengths, many normal-looking ellipticals reveal violent and intricate histories. What appears placid in starlight may, in reality, be a galaxy at war with itself, jets ripping through gas, wings flaring from old outbursts, a black hole silently reshaping its host. Perhaps in the future, we'll need a multispectral classification system, one that combines radio, X-ray, and optical morphologies to fully describe a galaxy's identity. And in such a system, the XRG might be one of the most informative types, a marker of galactic trauma, change, and cosmic memory. The study of X-shaped radio galaxies also invites deeper questions about cosmic symmetry and entropy. Why do some galaxies form near-perfect X-shapes while others veer into asymmetry? Is it merely randomness in orientation and timing, or is there an underlying principle that governs these patterns? The jets themselves are highly directional and energetic, yet their remnants, the wings, are more diffuse and chaotic. It's a cosmic metaphor for the arrow of time, sharp and defined at the moment of creation, blurred and softened as time marches forward. Some theorists have even proposed speculative ideas tying XRGs to deeper cosmic frameworks. Could they be natural laboratories for testing the holographic principle, where information on the event horizon of a black hole is encoded in these vast outflows? Or could the wing structures contain traces of interactions with primordial magnetic fields, relics from the earliest epochs of the universe? These ideas remain on the edge of current understanding, but XRGs continue to be excellent candidates for exploring the limits of known physics. It's also worth noting the cultural and philosophical power of these objects. To look at an X-shaped radio galaxy is to confront a story written in the language of the universe itself. No human made this. No civilization sculpted those jets. Yet the structure is so ordered, so elegant, that it evokes art. In a very real sense, XRGs are natural mandalas, geometric expressions of cosmic balance and imbalance, drawn not in sand, but in electrons and plasma across interstellar space. They remind us of the immense scales at play in the universe, not just in distance, but in time, energy, and transformation. A jet that stretches 800,000 light-years means the light from its tip began traveling to us when early humans were just beginning to use fire. And the energy required to create such a feature? It dwarfs the output of every star in the Milky Way combined. Yet despite this magnitude, we are able to see, measure, and begin to understand it. That is the triumph of astronomy, not merely observing the cosmos, but extracting meaning from its wildest phenomena. And there is still more meaning to be uncovered. As new observations come in, the models will evolve. Some theories will fall away, others will be refined, and entirely new ones may emerge. It's possible that the current taxonomy of radio galaxies will be upended, and the X-shape will no longer be considered exceptional, but a normal part of galactic evolution. Or perhaps we will find that the X-shaped structure is the cosmic equivalent of a transitional fossil, rare, fleeting, but incredibly informative about the forces that shaped everything we see. Whatever the outcome, one thing is clear: the study of X-shaped radio galaxies is not just a footnote in the story of astronomy. It is a chapter unto itself, full of mystery, insight, and cosmic drama, waiting for future generations of scientists, explorers, and thinkers to read deeper into its sprawling, symmetrical, interstellar script. Delving deeper into the intricacies of X-shaped radio galaxies brings us face to face with some of the most fundamental questions in astrophysics. What governs the life cycles of supermassive black holes? How do these titanic entities interact with their host galaxies and environments? And perhaps most intriguingly, what does the existence of XRGs reveal about the dynamic, ever-changing nature of our universe? One particularly fascinating aspect of these galaxies is the way their jets carry the fingerprints of their central black holes' histories. The orientation, strength, and morphology of jets are tightly linked to the spin axis and feeding behavior of the black hole. When a black hole's spin axis shifts, whether due to mergers, accretion disk instabilities, or other cosmic events, the jets trace out this change in space. The X-shape thus becomes a three-dimensional record of violent cosmic realignment, frozen in the energetic plasma streams traveling at near light speed. This cosmic memory, encoded in radio lobes, not only offers clues about the black hole's past but also influences the future of the host galaxy. Jets can clear gas out of galactic centers, quenching star formation and regulating the growth of the galaxy. But when jets reorient, they can ignite new regions, triggering starbursts or stirring the intergalactic medium. The X-shaped morphology, in this sense, symbolizes the balance between destruction and creation on a cosmic scale. Technological advances have been pivotal in unveiling these structures. Decades ago, the very detection of radio lobes was a groundbreaking achievement, unveiling the invisible side of the universe. Today, with sensitive arrays and sophisticated algorithms, astronomers can map the faintest wings extending hundreds of thousands of light-years beyond their galaxy's stellar disks. Detailed polarization studies reveal magnetic field configurations within the lobes, shedding light on the particle acceleration processes fueling these cosmic jets. Furthermore, XRGs serve as a natural laboratory for testing the limits of physics. They provide empirical data for understanding relativistic jet dynamics, magnetohydrodynamics, and black hole feedback mechanisms. By simulating the formation and evolution of XRGs under various conditions, astrophysicists refine models that are applicable not only to these peculiar galaxies but to a wide range of active galactic nuclei, AGN. Another layer of mystery involves the environments these galaxies inhabit. XRGs are often found in dense clusters or groups where galactic interactions and mergers are more frequent. The intergalactic medium in these regions can influence jet propagation, sometimes bending, distorting, or confining the lobes. Investigating the interplay between jets and their environments helps us understand the broader ecosystem of galaxy clusters and the cosmic web. The future of X-shaped radio galaxy research is incredibly promising. The upcoming James Webb Space Telescope, JWST, although primarily infrared, can provide complementary data on the stellar populations and dust content of host galaxies. Meanwhile, next-generation radio telescopes like the SK will dramatically increase the number of known XRGs, enabling statistical studies of their properties, evolution, and relationship to cosmic structures. In addition, gravitational wave observatories such as LISA, Laser Interferometer Space Antenna, may soon detect signals from supermassive black hole mergers, events potentially responsible for the jet reorientations producing XRGs. Correlating gravitational wave events with electromagnetic observations of XRGs could unlock unprecedented insights into black hole dynamics and galaxy evolution. Ultimately, X-shaped radio galaxies are not mere curiosities but vital threads in the tapestry of cosmic history. They embody the extraordinary interplay between gravity, magnetism, and high-energy astrophysics. They reveal the hidden lives of supermassive black holes and their profound influence on the universe. As we continue to study them, we not only uncover the secrets of these enigmatic structures but also deepen our understanding of the cosmos itself, its origins, evolution, and boundless complexity. The enigmatic X, etched across millions of light years, beckons us to explore, question, and marvel at the universe's most spectacular mysteries. Its story is far from complete, and with every new observation and discovery, we take another step closer to unraveling the profound cosmic dance it represents. Beyond the astrophysical mechanisms and observational details, X-shaped radio galaxies also compel us to rethink the narrative of galactic life cycles. Traditionally, galaxies have been viewed in fairly linear terms, forming stars, evolving morphologically, and sometimes undergoing energetic outbursts associated with their central black holes. But the XRG phenomenon illustrates a far more dynamic, sometimes chaotic evolution, where galaxies can experience abrupt shifts in their energetic output and structural orientation. One area ripe for exploration is the timescale over which these transformations occur. How quickly can a black hole spin axis reorient and produce the telltale X shape? Are we witnessing events that happen over millions of years, or could more rapid processes be at play? Current models suggest that black hole mergers and spin flips take place over millions to tens of millions of years, but ongoing studies are probing the possibility of more sudden shifts, perhaps triggered by disk instabilities or interactions with companion galaxies. Moreover, the fact that XRGs represent only a small fraction of all radio galaxies hints at their transient nature. This fleeting existence means we are catching them in a relatively rare phase of their evolutionary path, akin to seeing a butterfly in its chrysalis before it transforms. This rarity amplifies their value as cosmic laboratories. They provide snapshots of key transition points in the life of massive galaxies and their central engines. Delving into the plasma physics inside the lobes and wings further enriches the mystery. These structures are composed of charged particles accelerated to relativistic speeds, spiraling along magnetic field lines and emitting synchrotron radiation observable at radio wavelengths. The polarization and spectral index of this radiation encode information about the magnetic field strength, particle energy distributions, and the age of the plasma. Such measurements enable astrophysicists to reconstruct the history of jet activity, when jets switched off, when the wings formed, and how energy dissipated over time. Intriguingly, some X-shaped galaxies show evidence of multiple epochs of jet activity, suggesting that their central black holes may flicker on and off, or reorient jets multiple times throughout their lives. This episodic behavior challenges the idea of continuous jet activity and points to a complex interplay between black hole fueling, spin dynamics, and galactic environment. On the theoretical front, simulations incorporating magnetohydrodynamics and general relativity are increasingly sophisticated, allowing researchers to model jet formation and propagation with unprecedented detail. These simulations not only reproduce observed X-shaped morphologies but also predict how varying black hole spins, accretion rates, and environmental factors influence jet behavior. They help answer questions such as, how do jets carve paths through uneven interstellar media? What conditions favor stable X-shaped wings over more chaotic outflows? Can jet precession create overlapping or nested wing structures? Beyond the realm of radio observations, multi-wavelength studies are vital. XRG host galaxies are often massive ellipticals with complex histories of mergers and interactions. Optical and infrared imaging reveal stellar populations, dust content, and evidence of past collisions. X-ray observations detect hot gas halos and can identify shocks caused by jet interactions with the intergalactic medium. Together, these datasets weave a comprehensive picture of how the galaxy's structure and environment influence the spectacular radio morphology. The potential connections between XRGs and galaxy clusters are also profound. Clusters of galaxies contain vast reservoirs of hot, ionized gas, an environment that can channel, confine, or distort jets. Some XRGs are found at cluster centers, where the density and pressure of the intracluster medium strongly affect jet dynamics. In such environments, feedback from jets regulates cooling flows and star formation rates, impacting the cluster's evolution on large scales. More speculative theories have suggested exotic physics may be at play. For instance, some researchers have considered whether XRG wings could arise from interactions with dark matter halos or whether subtle violations of known physics might manifest in jet behavior. Though these ideas remain on the fringes, they underscore the potential of X-shaped radio galaxies as natural probes of the universe's fundamental laws. From a cosmic perspective, XRGs stand as testament to the violent beauty and complexity of galaxy evolution. They are reminders that the universe is not static but a dynamic arena where matter, energy, and gravity engage in endless dance, sculpting forms both elegant and enigmatic. Each X-shaped galaxy is a story, a puzzle piece in the grand mosaic of cosmic history. As we peer deeper into the cosmos with ever more powerful telescopes and sophisticated models, the secrets of X-shaped radio galaxies beckon us forward. They challenge our theories, inspire new questions, and fuel the timeless human drive to understand our place in the universe. The journey to unravel their mysteries is ongoing, a voyage across time, space, and the very fabric of reality itself. The profound enigma of X-shaped radio galaxies is deeply intertwined with the fundamental mechanics of supermassive black holes and their interplay with cosmic environments. At the core of these galaxies lies a supermassive black hole, millions to billions of times the mass of our Sun, whose gravitational grip orchestrates the symphony of matter and energy on a galactic scale. This black hole acts like a cosmic dynamo, pulling in matter from its surroundings and launching twin jets of charged particles at relativistic speeds. The shape, direction, and power of these jets are not arbitrary. They reflect the black hole's spin axis, the geometry of the accretion disk, and the dynamics of the black hole's merger history. When these elements undergo shifts, the jet's orientation changes, sometimes drastically, resulting in the X-shaped morphology that has captivated astronomers worldwide. Exploring how these massive black holes acquire such dramatic spin reorientations is key to understanding XRGs. One leading hypothesis involves galaxy mergers, the cosmic collisions of two galaxies, each harboring its own supermassive black hole. As these black holes spiral inward and eventually merge, their combined angular momentum can reorient the spin axis of the resultant black hole. This spin flip, or realignment, changes the direction of the jets suddenly, creating new lobes in a different direction while the old lobes remain visible, forming the characteristic X. This idea connects the large-scale morphology of radio jets directly to the violent processes that govern galactic assembly and black hole growth, highlighting the dynamic and sometimes chaotic nature of cosmic evolution. But this explanation only scratches the surface. Not all XRGs fit neatly into the merger-induced spinflip model. Some exhibit wings with unusual spectral and polarization properties that suggest more gradual or complex formation mechanisms. For instance, hydrodynamic backflow models propose that the wings arise not from jet reorientation but from the way material flows back along the sides of the active lobes, redirected by the shape and pressure gradients of the surrounding intergalactic medium. In this scenario, the X-shape is a natural consequence of how relativistic plasma behaves when it encounters obstacles or pressure boundaries, rather than a direct result of black hole spin changes. These competing models demonstrate how multifaceted and nuanced the interpretation of XRGs must be, pushing astronomers to integrate observations, theory, and simulations in innovative ways. The wings themselves, those faint, extended structures extending away from the primary jets, offer an intriguing window into plasma physics under extreme conditions. These lobes are reservoirs of relativistic electrons and magnetic fields, slowly fading as particles lose energy via synchrotron radiation. The spectral aging of these lobes, determined by measuring the radio emission at different frequencies, helps astrophysicists estimate how long ago the jets were active in a given direction. Wings that are older than active lobes indicate that jet reorientation occurred, while similar spectral ages suggest alternative wing formation processes. This detailed spectral mapping is a powerful tool for reconstructing the timeline of jet activity, revealing episodic patterns and potential environmental influences on jet propagation. On a more microscopic scale, the study of XRGs informs our understanding of magnetic field generation and structure in the universe. Jets and lobes are threaded by intense magnetic fields, crucial for the acceleration and collimation of the plasma streams. Polarization studies allow scientists to map the magnetic field direction and strength within the lobes and wings, revealing tangled or ordered structures shaped by interactions with the interstellar and intergalactic medium. These magnetic configurations affect how energy is transported, how particles are accelerated, and ultimately, how the jets influence their host galaxy. The complexity of these fields also poses fundamental questions about magnetohydrodynamics, MHD, in relativistic regimes, questions that are difficult to address with terrestrial experiments but accessible through astrophysical observations. Delving into the environments where XRGs reside reveals another layer of complexity. These galaxies are often situated in dense galactic clusters or groups, environments teeming with hot gas, dark matter, and neighboring galaxies. The intracluster medium, ICM, a hot, diffuse plasma permeating clusters, exerts pressure on radio lobes and can bend, confine, or disrupt the jets. This interaction shapes the final morphology of radio structures and may even trigger secondary wing formation through shock waves or turbulence. Understanding these environmental effects requires synthesizing data across the electromagnetic spectrum, from X-ray observations probing the hot gas, to radio maps tracing the jets, to optical and infrared studies revealing the host galaxy's stellar content and merger history. One of the most fascinating challenges is disentangling cause and effect in this cosmic interplay. Do the jets reshape the surrounding medium, or does the medium dictate the jet's morphology? In many cases, it is likely a feedback loop. Jets inflate cavities and heat the intracluster gas, preventing runaway cooling and star formation, while the density and motion of that gas influence jet direction and stability. This feedback mechanism is a cornerstone of modern galaxy evolution theory, and XRGs provide an extreme example where jet realignment adds new dynamism to the cycle. While the classical models of jet reorientation and hydrodynamic backflow account for many features of XRGs, alternative or complementary theories continue to emerge. Some researchers propose that complex accretion disk instabilities, warping under the influence of gravitational or magnetic torques, could produce jet precession or sudden flips without the need for black hole mergers. These instabilities may be triggered by variable feeding rates or interactions with infalling gas clouds. Such models emphasize the internal physics of the black hole accretion disk system rather than external merger events, broadening the scope of possible explanations. In addition, the role of binary black holes themselves is an area of active research. Before coalescing, two supermassive black holes orbiting each other can induce jet precession, leading to helical or curved jet paths visible in radio maps. These precessing jets can mimic or complicate the formation of X-shaped features. Observing these systems could offer a glimpse into the process of black hole mergers and the gravitational waves they produce, connecting radio astronomy with the burgeoning field of gravitational wave astrophysics. The observational challenges in studying XRGs are substantial. These galaxies are relatively rare and often distant, requiring sensitive radio telescopes with high spatial resolution to resolve their intricate structures. The advent of powerful facilities such as the Very Large Array, VLA, the Giant Meter Wave Radio Telescope, GMRT, and soon the Square Kilometer Array, SKA, is revolutionizing this field. These instruments can detect faint radio emissions, map polarization with precision, and survey large portions of the sky to identify new XRG candidates. With increasing data, statistical studies can uncover correlations between XRG properties and host galaxy characteristics, shedding light on their formation and evolution on a population level. The multi-wavelength approach is crucial. XRG hosts are primarily elliptical galaxies, often massive and old, but multi-wavelength observations reveal surprising complexities such as signs of recent mergers, star formation bursts, and active galactic nuclei variability. Infrared and optical spectroscopy can trace stellar ages, chemical composition, and gas dynamics, painting a detailed portrait of the galaxy's evolutionary path. X-ray data reveal hot gas halos and can detect shock fronts caused by jet interactions, providing insight into the energetic impact of jets beyond the radio realm. One cannot discuss XRGs without considering their place in the grander cosmological framework. They serve as cosmic beacons illuminating the interplay between gravity, magnetism, and relativistic plasma physics. Their study helps refine our understanding of black hole demographics across cosmic time, the frequency and consequences of galaxy mergers, and the role of AGN feedback in regulating galaxy growth. In this way, XRGs are microcosms of cosmic evolution, encapsulating themes that resonate across billions of years and billions of light years. As technology and theory advance, the possibility of detecting electromagnetic signatures of black hole spin flips in real time or near real time tantalizes astronomers. Such detections would provide direct evidence linking black hole dynamics with jet reorientation, transforming theoretical models into observable phenomena. Moreover, the synergy between electromagnetic and gravitational wave astronomy promises a new era in understanding supermassive black holes, with XRGs potentially serving as markers of past mergers whose gravitational waves we might detect. The complexity of XRGs also invites philosophical reflection on how we interpret cosmic phenomena. These galaxies remind us that the universe is not a simple, predictable machine but a dynamic, evolving tapestry woven from chaos and order. The interplay of forces, gravity's relentless pull, magnetic fields' guiding hands, and the dance of matter and energy near black holes, creates structures that challenge our models and inspire deeper inquiry. Intriguingly, X-shaped radio galaxies also raise questions about the limits of human observation. Their faint wings often push the boundaries of current telescope sensitivity, meaning many such galaxies may remain undiscovered. The future, with more sensitive arrays and advanced data processing techniques powered by artificial intelligence, holds the promise of unveiling a far richer population of these cosmic X's, providing a statistically robust sample to unravel their mysteries more completely. Additionally, XRGs provide a unique window into relativistic astrophysics, a regime where velocities approach the speed of light, and magnetic fields channel energetic particles across enormous distances. Understanding how these jets remain collimated over hundreds of thousands of light-years challenges our grasp of plasma stability and turbulence in extreme environments. These insights have implications beyond astrophysics, informing plasma physics and magnetohydrodynamics relevant to laboratory experiments and fusion research. The energetic feedback from jets and XRGs also influences their host galaxies in profound ways. By heating or expelling gas, jets can suppress star formation, regulating the galaxy's growth and shaping its evolutionary trajectory. This feedback mechanism helps explain why massive galaxies often cease star formation early in their histories, transitioning into quiescent ellipticals. The reorientation of jets and XRGs adds temporal and spatial complexity to this feedback, potentially impacting different regions of the host galaxy over time. The study of X-shaped radio galaxies exemplifies the interdisciplinary nature of modern astrophysics. It combines observational astronomy, theoretical physics, computational simulations, plasma physics, and cosmology. Each discovery about XRGs reverberates across these fields, enriching our collective understanding of the cosmos. As we continue to peel back layers of these enigmatic structures, we not only solve puzzles about particular galaxies but also advance our grasp of the universe's grand design. The story of X-shaped radio galaxies is far from complete. They stand as cosmic enigmas, symbols of the universe's capacity to surprise and astound. Each new observation, each refined model, and each technological leap brings us closer to comprehending these spectacular structures. Their study is a testament to human curiosity and the relentless quest to understand the cosmos in all its complexity and wonder. Understanding the distribution and frequency of X-shaped radio galaxies, XRGs, across cosmic time is a critical next step in their study. These peculiar galaxies are relatively rare, suggesting that the conditions necessary for their formation, such as major galaxy mergers or specific environmental influences, are not commonplace, or at least not always visible in radio emissions. Surveys that catalog radio galaxies at different redshifts can help trace the evolutionary timeline of XRGs. If they appear more frequently at earlier epochs in the universe, it might imply that galaxy mergers and chaotic black hole dynamics were more common during those formative cosmic periods. Conversely, if they persist uniformly across time, it may indicate an underlying, enduring mechanism that occasionally flips the spin axis of black holes regardless of cosmic age. The morphology of XRGs also challenges classification systems within radio astronomy. Traditional radio galaxies are typically classified into two Fanneroff-Rayleigh types, FRI, with jets that fade and broaden with distance from the galaxy core, and FR2, with jets that remain collimated and terminate in bright hotspots. XRGs complicate this dichotomy. Some have FR2-type main lobes and fainter FRI-like wings, while others defy categorization entirely. This hybrid nature could suggest transitional phases in radio galaxy evolution or interactions between different formation mechanisms. As astronomers refine classification schemes to accommodate these complexities, XRGs become key players in shaping our broader understanding of radio galaxy taxonomy. From a computational perspective, simulations of X-shaped radio galaxies have become increasingly sophisticated, incorporating general relativistic magnetohydrodynamics, GRMHD, dynamic accretion processes, and realistic environmental models. These simulations are essential because they allow researchers to recreate possible jet reorientations, disk instabilities, and interactions with the intergalactic medium in controlled, testable environments. With ever-improving computing power, these simulations now achieve higher resolution and can explore parameter spaces once beyond reach. They can track the evolution of jets over millions of years, visualize how jets interact with asymmetric gas distributions, and show how magnetic fields respond to sudden changes in spin orientation. Another factor of interest is the energy budget of XRGs. Radio jets are some of the most powerful phenomena in the universe, and any reorientation implies a significant amount of energy being redirected. This raises the question, what does it take, energetically, for a supermassive black hole's spin axis to flip? Theoretical models suggest that massive mergers or dramatic changes in accretion flows are required, events that themselves release tremendous amounts of energy. Tracking this energy through multi-wavelength observations helps researchers determine whether observed features, like ghost lobes or faint wings, match the expected output from these violent shifts. Energy conservation also constrains which models are physically plausible. Interestingly, a number of XRGs exhibit asymmetry between their wings, with one appearing brighter, longer, or more sharply defined than the other. This asymmetry hints at additional environmental factors. Perhaps one side of the galaxy lies within a denser region of intergalactic gas, absorbing or deflecting the jet material more strongly. Or perhaps the wing's asymmetry reflects differences in age, as precession and backflow might operate more effectively in one direction than the other. These asymmetries provide valuable clues, and mapping them in large samples could reveal broader trends about cosmic environments and jet interactions. One compelling line of investigation concerns the relationship between XRGs and episodic AGN activity. Some radio galaxies exhibit signs of restarting their jet activity after a dormant phase, producing structures such as double-double radio galaxies, DDRGs, where newer, smaller lobes appear within older, faded ones. If jet reorientation happens between these active episodes, then the new jets would appear at different angles, potentially forming an X-shaped pattern. This episodic activity model posits that XRGs are snapshots of AGNs caught between cycles of activity and dormancy, revealing an evolutionary link between multiple radio galaxy types. Connecting XRGs with DDRGs could unify previously disconnected observations under a broader theory of intermittent AGN behavior. A separate avenue of inquiry explores whether XRGs may signal the presence of misaligned accretion disks. In most AGNs, the accretion disk aligns with the black hole's equatorial plane, and the jets are launched perpendicular to this disk. However, if the accretion disk forms from material with angular momentum misaligned with the black hole's spin, it could warp or even break into segments, a phenomenon predicted by the Bardeen-Pedersen effect. In this situation, the inner disk aligns with the black hole, while the outer disk maintains its original orientation. This misalignment can twist the jet direction over time, producing curved or multidirectional lobes. In extreme cases, the jet redirection could be sudden enough to create the appearance of an XRG. Such internal disk dynamics challenge the idea that external events like mergers are the sole causes of jet reorientation. Polarization studies also deepen our understanding of XRG structure. When radio waves pass through a magnetized medium, their polarization changes, a process known as Faraday rotation. By studying these polarization shifts, scientists can reconstruct the magnetic field configurations within and around radio galaxies. XRGs often exhibit distinct polarization patterns in their wings compared to their main lobes, supporting the notion that different processes or timescales shaped each component. Some wings show low polarization, possibly due to turbulence or interactions with dense ambient gas, while others are highly polarized, indicating more ordered magnetic fields. These polarization fingerprints act like cosmic fingerprints, revealing the life history of each lobe. Moreover, the presence of large-scale X-shaped structures may impact star formation in the host galaxy. Jets can quench star formation by heating or ejecting cold gas, but they can also compress gas clouds and trigger starbursts under the right conditions. If XRGs represent instances where the direction of feedback changes over time, they might influence star formation in more complex, patchy, or prolonged ways than conventional jets. Studying XRG host galaxies in ultraviolet and infrared bands, where young stars are most visible, can reveal whether these galaxies are actively forming stars or have been quenched by previous jet episodes. Recent observations using LOFAR, the Low Frequency Array, and the VLA have begun identifying a new subclass of radio galaxies with complex morphologies that resemble partial or distorted X-shapes. Some of these galaxies might be failed XRGs, where jet reorientation began but was cut short or stifled by environmental resistance. Others could represent different stages of evolution, with wings that have faded below the detection threshold at higher frequencies. LOFAR's low-frequency sensitivity excels at finding these older, dimmer structures, potentially revealing a much larger population of winged radio galaxies and suggesting that XRG-like behavior is more common than previously believed. Intriguingly, some researchers have proposed that XRGs might serve as indirect evidence of gravitational wave emission. When two supermassive black holes merge, they release a burst of gravitational waves. If this merger is asymmetric, the remnant black hole could experience a recoil kick, physically moving it within the host galaxy and altering its spin orientation. Such a kick might also trigger a change in jet direction, producing the X-shaped signature. Although we cannot yet directly observe these gravitational waves at nanohertz frequencies, radio observations of XRGs might offer a tantalizing clue to their occurrence. In this way, XRGs could serve as radio beacons marking the aftermath of gravitational wave events. Another speculative yet fascinating possibility is that the reorientation of jets in XRGs could help test theories of black hole spin alignment and evolution in hierarchical models of structure formation. In models where black holes grow through continuous accretion rather than mergers, their spin axes should gradually align with their host galaxy's angular momentum. But the presence of XRGs suggests abrupt, even violent changes in orientation, favoring models where black holes undergo significant disruption during their growth. These observations may help resolve debates about whether black holes spin up through steady feeding or are shaped by chaotic events in their histories. As astronomers look toward the future, the Square Kilometre Array, SKA, promises to revolutionize the study of XRGs. With unmatched sensitivity and sky coverage, SKA will detect fainter and more distant radio lobes, providing a statistically robust sample of XRGs across cosmic time. This will enable precise measurements of their frequency, distribution, and environmental context. Combined with advanced machine learning techniques for morphology classification, researchers will be able to identify subtle jet deviations and uncover early or partial XRG candidates that may currently go unnoticed. The interplay of observations and theory is reaching a new crescendo. Data from SKA, VLA, LOFR, and Chandra will be cross-referenced in real time, allowing astronomers to simultaneously analyze radio structure, X-ray environment, host galaxy features, and even potential optical variability. This holistic view will help untangle whether XRGs are a single phenomenon with many expressions or a family of related but distinct galactic behaviors. The outcome could redefine how we interpret radio morphology entirely, shifting the field from static classification to dynamic histories. Beyond the scientific realm, X-shaped radio galaxies continue to capture the imagination. They embody the cosmic drama of violent mergers, spinning giants, and intergalactic fireworks. Their distinctive shape, a cross carved into the fabric of space, evokes symbolism as much as science. They stand as reminders that the universe is not only governed by equations and energy but also shaped by collisions, chance, and change. Each X in the sky is a frozen moment in a celestial story billions of years in the making, now unfolding through the lenses of human ingenuity and curiosity. One of the enduring questions about X-shaped radio galaxies is whether their wings are the result of actual jet redirection or simply a passive hydrodynamic phenomenon. This difference isn't trivial. It speaks to the fundamental mechanisms of how galaxies evolve and interact with their surroundings. In the redirection model, the black hole's spin axis physically shifts, perhaps through merger events or the ingestion of misaligned gas. In the hydrodynamic backflow model, on the other hand, the wings form as the relativistic plasma from the jets flows backward along paths of least resistance, shaped by pressure gradients in the surrounding medium. Determining which mechanism dominates requires not only high-resolution radio images but also detailed modeling of the gas density, pressure, and magnetic field configurations surrounding the host galaxy. The observational evidence remains mixed, with some XRGs exhibiting symmetrical wings suggestive of a central origin and others showing skewed or curved wings indicative of environmental shaping. A particularly intriguing line of study involves XRGs located in galaxy clusters or groups, environments rich in hot gas and gravitational complexity. In these crowded cosmic neighborhoods, radio jets may be easily deflected, slowed, or redirected by interactions with the intergalactic medium, or even with nearby galaxies. In such scenarios, the X morphology might not be the result of intrinsic processes within the AGN, but rather a consequence of extrinsic environmental conditions. This opens up a wider framework for understanding XRGs, not as standalone anomalies, but as emergent features arising from the galaxy's broader cosmic context. Observations with the Chandra X-ray Observatory have helped map the hot gas in these clusters, showing cavities, shocks, and asymmetries that could correlate with wing formation. Another clue to the puzzle lies in the relative ages of the lobes. If we can estimate how long ago each set of lobes was formed, we can better understand the timing and sequence of events that shaped the X structure. Radiospectral aging techniques allow researchers to estimate the age of relativistic electrons in the lobes by analyzing how their energy distribution changes over time due to synchrotron losses. In many XRGs, the wings appear older than the active lobes, suggesting a sequence in which an older jet orientation was replaced by a newer one. However, the exact time scales remain uncertain. Are we seeing changes over millions of years, or tens of millions? The answer has implications for how quickly black hole spins can shift and for how long jet structures can persist in the intergalactic medium. The central engines of XRGs, supermassive black holes, are not just passive gravity wells but dynamic, spinning objects with angular momentum that plays a key role in jet formation. The spin of a black hole influences the efficiency with which it can convert accreted matter into energy and launch relativistic jets. If the spin axis shifts due to a merger or the ingestion of angular momentum from misaligned accretion flows, the direction of jet ejection can also change. But spin changes are not trivial events. They involve vast amounts of energy and momentum transfer. This process is likely mediated by phenomena such as the Bardeen-Pedersen effect, length-stirring precession, and relativistic frame dragging. These are not merely theoretical constructs. They're grounded in Einstein's general relativity and observed in other astrophysical systems, like the precession of accretion disks around stellar mass black holes. The role of magnetic fields in jet redirection also deserves attention. Magnetic fields are crucial for jet collimation and stability, and they may also play a role in determining whether a jet can maintain a coherent direction during a spin flip event. If the magnetic field is strong and anchored in the inner accretion disk, it may resist changes in orientation, potentially leading to internal stress, disk warping, or even jet disruption. Conversely, if the field is weaker or more tangled, it may realign more easily with a new black hole spin axis, allowing the jet to quickly reorient. These magnetic dynamics are being explored in magnetohydrodynamic simulations, which show that jet direction can be quite sensitive to the geometry and strength of magnetic field lines at the black hole's poles. Some researchers have begun to look for potential gravitational wave signatures in galaxies suspected of recent mergers that could have produced XRGs. While direct detection of gravitational waves from supermassive black hole mergers remains beyond our current reach, indirect signals such as disturbances in star distribution, asymmetries in stellar motion, or offset AGNs could serve as circumstantial evidence. The idea is that if XRGs result from spin flips caused by black hole coalescence, there should be telltale dynamical scars left in the host galaxy structure. These could include displaced cores, double nuclei, or stellar streams from disrupted orbits. By combining radio, optical, and spectroscopic data, researchers can search for these hidden relics of cosmic upheaval. One exciting direction in XRG research involves time-domain astronomy. Although the timescales involved in jet redirection are far beyond human observational lifespans, variability in the radio flux of AGNs can offer real-time clues about the behavior of the central engine. Sudden flares, quiescent phases, or changes in polarization may indicate instabilities in the accretion disk or transitions between jet modes. By monitoring known XRGs over long periods, astronomers might catch signs of ongoing activity or dormant jets reigniting. These data can help differentiate between ongoing dynamic processes and fossil relics of past behavior. Machine learning is also beginning to make its mark in the study of XRGs. With sky surveys producing petabytes of data, traditional classification methods are no longer sufficient. Algorithms trained on labeled images can now identify candidate XRGs with high precision, even when the structures are faint or partially obscured. These systems can also identify outlier morphologies that might represent new subclasses of winged galaxies or transitional forms. As the volume of data grows with instruments like the SKA, these tools will be indispensable for cataloging the full diversity of XRG-like phenomena and for refining our theoretical models in light of a more comprehensive observational dataset. There is also growing interest in exploring the role of galaxy morphology in XRG formation. Are elliptical galaxies more likely to host XRGs than spirals? Do bars, bulges, or other structural features correlate with the presence of wings? Early studies suggest that XRGs tend to reside in massive elliptical galaxies, which are more likely to have undergone major mergers and possess large central black holes. However, the sample size is still small, and ongoing surveys may reveal a more nuanced picture. Understanding the host galaxy structure and history is key to determining whether internal dynamics or external interactions are more important in shaping XRGs. At a more fundamental level, XRGs challenge our understanding of symmetry and directionality in the universe. The X structure suggests not just a change in direction, but a kind of multidirectional past, a history written in two axes rather than one. In a cosmos where energy is typically funneled along single, focused lines, the presence of orthogonal or intersecting jet paths implies a break from equilibrium. This kind of deviation from expected behavior is often where new physics or deeper understanding emerges. In that sense, every XRG is like a cosmic riddle, one whose answer may reshape how we think about time, momentum, and cause in astrophysical systems. Interestingly, some XRGs are associated with low-luminosity AGNs, which seem to contradict the idea that powerful black hole activity is required to sculpt vast radial lobes. This raises the possibility that the wings we see today were formed during an earlier, more active phase, and that the central engine has since quieted. Alternatively, it may suggest that even relatively weak jets can generate significant structure if given enough time or the right conditions. This adds a layer of complexity to our models, indicating that jet power alone may not be the only determining factor in wing formation. It could be a combination of jet duration, environment, and prior activity history. There are also rare examples of triple-lobed radio galaxies, where a central lobe is flanked by two symmetric side lobes at an angle. Some astronomers suggest that these may be transitional forms between standard radio galaxies and fully developed XRGs. Others propose that they represent separate phenomena entirely, possibly involving binary AGNs with competing jets or sequential reorientation events. In any case, they expand the morphological zoo and challenge our neat categorizations. They serve as reminders that nature doesn't always conform to our labels and that reality is often more complex than our theories. Efforts to map the large-scale distribution of XRGs across the sky are still ongoing, but preliminary results indicate they are not randomly distributed. Instead, they may cluster in certain cosmic filaments or voids, hinting at a relationship between large-scale structure and jet dynamics. If confirmed, this would suggest that the orientation and behavior of jets are influenced not just by local conditions, but by the galaxy's position within the cosmic web itself. This raises profound questions about whether cosmic structure guides the directionality of galactic activity, and how much agency supermassive black holes truly have in determining their own fate. XRGs serve as a powerful metaphor for the changing nature of science itself. Once considered oddities, these galaxies are now recognized as keys to understanding some of the universe's deepest processes. Their very strangeness has forced astronomers to refine their models, question assumptions, and broaden their investigative horizons. In a way, they remind us that discovery often begins at the margins, at the edges of symmetry, predictability, and familiarity. They're not just cosmic curiosities, they're indicators of the universe's hidden complexities, waiting to be decoded one lobe at a time. The enigmatic nature of X-shaped radio galaxies extends even to their apparent scarcity. Despite decades of surveying the skies, astronomers have identified only a few hundred of these galaxies among the tens of thousands of known radio-loud AGNs. This statistical rarity suggests that either the specific conditions required for their formation are uncommon, or that their X-shaped morphology is fleeting, visible only during a narrow temporal window in a galaxy's evolution. Some astrophysicists propose that many galaxies may go through an XRG phase, but the wings fade quickly or are masked by surrounding noise, making them difficult to detect unless caught at just the right moment. This line of thinking implies that the universe might be full of hidden XRGs, ghosts of previous galactic behaviors, just waiting to be uncovered with more sensitive instruments. As observational technology improves, so too does our capacity to detect faint and extended radio structures. Next-generation radio telescopes like the Square Kilometre Array, (SK), the Very Large Array Sky Survey, (VLAS), and LOFAR are already reshaping our view of the radio universe. These observatories offer increased sensitivity and resolution, allowing astronomers to detect the subtle emissions of older or more distant X-shaped structures that previously went unnoticed. With such tools, the study of XRGs is poised to enter a new era, where statistical samples grow large enough to allow population studies and correlations with other galactic properties. This could finally reveal the frequency and circumstances under which these mysterious morphologies emerge. There's also the question of how jet dynamics relate to dark matter halos, the invisible cocoons that surround galaxies and influence their evolution. Some theorists have proposed that the shape and density of a galaxy's dark matter halo could affect the propagation of radio jets. In non-spherical or triaxial halos, pressure gradients might deflect or compress jets in nonlinear ways, potentially contributing to the formation of off-axis lobes. If true, this would mean that the visible X structure is not only a clue to black hole dynamics, but also a visible trace of the invisible scaffolding of dark matter. Studying XRGs in this context could therefore offer a novel method of probing dark matter's influence on baryonic processes, one of the most elusive goals in modern astrophysics. Meanwhile, the role of cosmic magnetic fields continues to emerge as a crucial component in the grand ballet of jet formation and propagation. In the context of XRGs, these fields may not just guide the jets but actively shape their trajectory through feedback mechanisms. Magnetic reconnection events, field instabilities, and turbulent eddies could all alter the symmetry of lobe expansion. Understanding how these invisible lines of force interact with relativistic particles could help explain why some wings appear sharply defined while others seem diffuse or asymmetric. Advanced polarization studies, capable of mapping the magnetic field structure in and around radial lobes, are beginning to reveal intricate patterns that were once impossible to discern. XRGs may also play a hidden role in galaxy feedback processes, particularly in regulating star formation. In massive galaxies, jets from active black holes can inject vast amounts of energy into their surroundings, heating the gas and preventing it from cooling and collapsing into new stars, a process known as AGN feedback. The X-shape may represent a particularly effective geometry for this feedback, as wings could distribute energy more isotropically across the intergalactic medium. If true, this morphology could be a crucial component in galactic evolution models, especially for massive ellipticals where quenching of star formation is most evident. In this view, the X-shape is not just an observational curiosity, but a central feature in the life cycle of galaxies. Another area of investigation lies in the chemical enrichment of the wings themselves. As relativistic jets plow through the intergalactic medium, they can carry with them high-energy particles and heavy elements from the galaxy's interior. The wings may thus act as conduits, transporting enriched material to large distances. Observing the elemental composition of these structures, though technically challenging, could provide insights into the internal makeup of galaxies and the processes by which they distribute their matter. In essence, the wings could be giant cosmic syringes, injecting energy and elements into the vast void of intergalactic space. The potential cosmological implications of XRGs are no less fascinating. If their formation is tied to black hole mergers, and if such mergers are common in hierarchical structure formation, then XRGs might serve as visual signposts of the universe's merger history. Their orientation, frequency, and distribution could encode a fossil record of how galaxies have assembled over cosmic time. In this sense, XRGs become a form of astrophysical archaeology, revealing not just local events but the broader tapestry of cosmic evolution. They are like the cosmic equivalent of ancient ruins, pointing to dramatic events long since past. Moreover, some researchers have speculated that XRGs might act as natural laboratories for testing alternative theories of gravity or space-time structure. Because their morphology is so strongly shaped by relativistic effects, any deviation from standard general relativity, such as modified gravity theories or the presence of extra dimensions, could leave observable imprints on their shape or dynamics. While still speculative, such possibilities highlight how astrophysical anomalies like XRGs can serve as probes of fundamental physics, reaching into domains where terrestrial experiments currently cannot. The potential for XRGs to be linked to binary supermassive black holes remains a tantalizing prospect. In galaxies that host more than one central black hole, either in a pre- or post-merger state, the competing gravitational fields and angular momentum vectors can create complex dynamical environments. Jets from such systems may precess, flicker, or abruptly change direction, potentially forming the characteristic X pattern over time. If confirmed, this would have implications not only for our understanding of galaxy mergers but also for the expected frequency of gravitational wave events detectable by pulsar timing arrays or future space-based observatories like LISA. The observational biases in current XRG catalogs must also be acknowledged. Most known examples come from surveys focused on relatively bright, nearby galaxies, often using instruments tuned to certain radio frequencies. This means that our current sample may be skewed towards certain types of XRGs, possibly missing out on fainter, more distant, or lower power examples. As newer surveys expand the observational window, both in depth and in spectral coverage, we may find that XRGs come in more varieties than we currently imagine. There could be mini XRGs, ultragiant XRGs, or even multi-winged structures that defy the simple X classification. The artistic and philosophical resonance of X-shaped radio galaxies shouldn't be ignored either. There's something uniquely striking about the X form, a shape that suggests balance, tension, and change all at once. In ancient cultures, the X symbolized crossroads, transitions, and often the unknown. In the cosmos, it takes on a similar meaning, a literal and metaphorical intersection of energies, histories, and forces. Each XRG stands as a symbol of transformation, a moment where the ordinary rules of galactic behavior were bent, reshaped, or redirected. What makes the mystery of XRGs particularly compelling is that they seem to sit at the intersection of so many cosmic processes: black hole dynamics, intergalactic feedback, magnetic field behavior, large-scale structure, and even the nature of space-time itself. They are not isolated puzzles but rather deeply integrated mysteries whose resolution may ripple across many domains of astrophysics. Solving the riddle of X-shaped radio galaxies could therefore unlock insights that go far beyond the galaxies themselves, reaching into the very fabric of how the universe organizes and transforms energy. It's worth pondering what future technology might reveal about these cosmic enigmas. Could ultra-high-resolution interferometers one day resolve the internal structure of the wings in exquisite detail, showing us the exact flow lines of plasma and magnetic fields? Might next-generation X-ray observatories detect shock fronts or cavities invisible to radio telescopes, giving us a layered view of how jets and wings interact with their surroundings? Or could artificial intelligence, trained on an ocean of multi-wavelength data, discover hidden patterns that elude even the most skilled human analysts? The future of XRG research promises to be as dynamic and multidimensional as the galaxies themselves. For now, though, we remain in the realm of questions, intrigued, puzzled, and humbled by the complexity of these extraordinary objects. They challenge our models, disrupt our assumptions, and demand a deeper engagement with the physics of extremes. In the mystery of the X-shaped radio galaxy, we find not just an astrophysical curiosity but a mirror to our own scientific journey, always reaching outward, always questioning, always trying to piece together the unseen story etched in the stars. The more we examine X-shaped radio galaxies, the more we realize they represent a crucible where cosmic violence and symmetry collide in unexpected ways. At first glance, the idea of jets of relativistic particles erupting from galactic cores and simply changing direction sounds improbable, yet that is precisely what the existence of these X-shaped structures implies. The lobes that branch off at sharp angles from the main axis do not appear chaotic or random. They exhibit remarkable symmetry, suggesting a precise choreography, even if we have yet to fully understand the conductor. It's as though the galaxy performed a pirouette, spinning its jets into new orientations while retaining the echoes of its previous state, ghosts of cosmic inertia frozen in space. One particularly captivating idea gaining attention involves the realignment of the central black hole's spin axis due to the coalescence of two supermassive black holes following a merger. When two galaxies collide and merge, their central black holes may spiral inward and eventually merge as well. The merged black hole could receive a gravitational recoil, or kick, that abruptly changes its orientation. Since relativistic jets align with the spin axis of the black hole, this realignment would manifest as a change in jet direction, thereby forming new lobes perpendicular or at sharp angles to the old ones. The older lobes become wings, while the new active jets form the arms of the X. This sudden transition captures a rare snapshot of cosmic reconfiguration, a before and after image on a galactic scale. Yet some models suggest a more fluid process, not a sudden spin flip, but rather a gradual precession of the jet axis. This precession could occur due to interactions with surrounding matter or as a consequence of binary black hole orbital dynamics. In such a case, the jets wouldn't jump to a new position, but slowly spiral over time, tracing a curved path and potentially producing multiple pairs of lobes. Indeed, some observed X-shaped galaxies appear to show more than 4 lobes, hints of past jet activity that oscillated between orientations, each one leaving a fading impression. These multiple-lobed galaxies suggest that jet direction is not fixed, but a dynamic quality influenced by complex internal mechanics and environmental pressures. This opens up the possibility of categorizing X-shaped radio galaxies by their morphology and inferred history. Some may be the result of sudden spin flips. Others might be products of slow jet precession. Still others could be shaped by hydrodynamic backflows, where material from the main jet rebounds and flows back toward the galactic center, deflecting into secondary directions. This backflow model has gained support due to its ability to explain the apparent symmetry in some wings, and the way they often appear less collimated and more diffuse than the primary lobes. The wings, in this view, are not new jets but redirected old ones, sculpted by invisible pressure gradients and the inertia of earlier ejections. One of the great challenges in unraveling the origin of XRGs is the difficulty in determining the age of the different lobes. If we could reliably measure the time elapsed between the formation of the wings and the active lobes, we might be able to determine whether we are looking at a sudden reorientation event or a more prolonged process. Techniques such as spectral aging, which analyze how the radio spectrum of synchrotron radiation evolves over time, offer some hope in this regard. The spectrum steepens as electrons lose energy, allowing astronomers to estimate how long ago the emission occurred. However, uncertainties in magnetic field strength, particle acceleration efficiency, and environmental conditions often complicate these estimates. The intergalactic medium plays a substantial, often underappreciated role in shaping the observable features of radio galaxies. In dense clusters, the surrounding gas and plasma can act as a viscous medium, resisting the outflow of jets and redirecting their paths. In lower density environments, jets can travel farther and more freely, possibly producing more extended wings. The variability of the intergalactic medium introduces another layer of complexity when comparing different XRGs. Two galaxies with identical black hole properties might exhibit vastly different radio morphologies simply because of differences in their cosmic neighborhoods. Adding another layer of intrigue is the possibility that X-shaped morphologies may evolve into other shapes over time. What appears as an XRG today might eventually resemble a standard double-lobed radio galaxy as its wings fade into invisibility. Conversely, a seemingly ordinary radio galaxy may once have been an XRG whose wings have since dissipated. This temporal fluidity challenges our ability to classify these objects rigidly, and instead encourages a more dynamic understanding, one where morphology is a function of age, environment, and internal physics, not merely static classification. The question of detection bias cannot be overstated. The angle at which we observe these galaxies plays a critical role in how their morphology appears. An X-shaped structure viewed head-on may appear as a single or double-lobed galaxy, hiding its true configuration from our view. Conversely, a standard radio galaxy observed at an oblique angle might be misinterpreted as an XRG. This underscores the need for 3D modeling and simulations to help interpret our 2D observations. Computer-generated reconstructions based on real data can help bridge the gap between appearance and reality, providing a more accurate understanding of the underlying structures. In recent years, machine learning has begun to play a vital role in the identification and classification of radio galaxies. Convolutional neural networks trained on labeled datasets can now sift through millions of images from radio surveys and flag candidate XRGs with remarkable accuracy. These AI tools are helping uncover previously unnoticed examples, many of which are faint or distorted, expanding our catalog and enabling more robust statistical studies. With continued training and refinement, such systems may even learn to differentiate between the various formation mechanisms, offering a new kind of diagnostic power that complements traditional analysis. Beyond their astrophysical implications, XRGs also raise profound philosophical and existential questions. They serve as visual testimonies to dramatic, unseen transformations, galaxies literally rewriting their histories in the sky. They speak to the impermanence of even the most massive cosmic entities, reminding us that change is the default condition of the universe. What we see in these galaxies are not static structures, but echoes of ancient violence, cycles of activity and dormancy, expressions of a universe that is alive, restless, and constantly in flux. There's also something hauntingly poetic about the time scales involved. The wings of an XRG might represent events that occurred millions of years ago, their radiation only now reaching our telescopes. We are, in a very real sense, looking into the past, witnessing relics of moments so ancient that even the galaxies themselves may have changed beyond recognition by the present day. The study of XRGs is thus a form of time travel, a way of catching cosmic events in the act, albeit long after they've occurred. It's a humbling reminder of our smallness in both space and time. Speculative theories continue to push the boundaries of our understanding. Some researchers have proposed that XRGs might be connected to more exotic phenomena, such as frame-dragging effects near spinning black holes, or even interactions with topological defects in space-time left over from the early universe. While these ideas remain fringe and largely untestable with current data, they highlight the sense of wonder and curiosity that XRGs evoke. The very fact that such ideas are entertained is a testament to the power of these enigmatic shapes to spark the imagination. On a more grounded level, one cannot ignore the immense energy involved in creating an XRG. The jets that carve out these structures move at relativistic speeds and carry energies that dwarf anything humanity could ever hope to generate. To reshape intergalactic space on such scales, a black hole must tap into vast reservoirs of gravitational energy, converting it into kinetic and electromagnetic outflows with extraordinary efficiency. Studying these processes provides critical insights into how nature harnesses energy in the most extreme conditions, a subject of interest not only for astrophysicists but also for theoretical physicists and engineers inspired by cosmic phenomena. There's a sense that we are only just beginning to grasp the full complexity of X-shaped radio galaxies. Every new discovery adds a piece to the puzzle, yet also raises new questions. Are there analogues of XRGs at other wavelengths, perhaps in the infrared, ultraviolet, or gamma-ray regimes, that we have yet to detect? Could similar processes be occurring in other cosmic contexts, such as neutron star mergers or quasars with unusual variability? Might XRGs be part of a broader class of transient or transitional galactic phenomena that includes other exotic forms like Z-shaped or S-shaped galaxies? Ultimately, the study of X-shaped radio galaxies embodies the essence of scientific inquiry, the interplay between observation, theory, imagination, and humility. They are strange and beautiful markers of cosmic evolution, silent yet eloquent witnesses to the turbulent histories of galaxies. In their bold, symmetrical arms, we find the imprint of collisions, alignments, displacements, and rebirths on incomprehensible scales. And as long as they continue to elude full explanation, they will inspire us to keep asking, keep looking, and keep wondering. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.